Yeah, hi, good evening, everyone. Welcome to the first revision session for quiz 2. So, today we will just discuss the conceptual questions based on the week 5 and week 6. I hope you have already solved the questions of mock. What we will just solve again. Okay, so the questions related to the week 5 and week 6 we will just discuss. And also, I have some previous terms questions quiz or end-term questions, so that we will also discuss from week 5 and week 6. So before starting the session, if anyone have any query, uh, any doubt from your side, so if you have any query in the and any questions, okay, so maybe you are also practicing on the previous terms quiz questions or end-term questions. So if you have any queries, so you can ask, okay, after completion of the questions. Okay. So, any query from anyone before starting the session?
Hello.
Yes, come. Yeah.
Sir, actually, what will be the syllabus up to week 8 only, na, sir?
Yes, up to week 8. And
And
mainly from week 5 to week 8.
okay, the weightage will be 70-80% from week 5 to 8 only.
You can say not 70, 80, totally 100% weightage from the week 5 to week 8. But actually, some topics are actually interrelevant from the previous week's topics.
Sir,
Okay, so like complexity, we are learning for the each algorithm. So the complexity is discussed in week 2. So by default,
sir,
it inherit the concept.
sir, is it required to clear this OPP of this PDSA, or we can go
No, no,
ahead
no.
if
No. Actually, that OPP contains only 20% weightage in total score, not the separate passing criteria required.
okay, now
Okay.
onwards. Okay, sir. Okay, sir.
Okay. So
And
if you
is this related with this placement and other activity also? If we are not securing good marks in programming OPP, then we are not eligible like that.
no, that's type of criteria we are not setting up any place for the placement things, but we just recommended that just practice, just give the OPP exam because it have 20% weightage, so definitely your score will be decreased in the PDSA. So if you totally skip this,
Sir, thank you, sir.
okay, so do not
Thank you.
skip this. Just try to attempt and try to solve it at most problem. Okay, so not maybe one, two, three, any problems which you can solve. Just try it.
Okay, sir.
So the answers of graded solved answers, can
Hmm.
you upload them?
So, answers for
The graded assignments.
your answer is already there.
No, I didn't find them in the supplementary.
No, that actually we are not releasing the solution as a PDF, but the some solution feedback is already configured on the portal. After
No, I'm talking about graded assignments, not about.
that feedback is also there. That feedback is also there. So let me just share my screen. One second. So after deadline, you can see the feedback of the question. So some solution related feedback.
That is along with the graded assignment only, but how it is solved is not there.
One second. Yeah. So let me just open any previous week. So I hope my screen is visible.
Yes, sir.
Okay. So graded assignment 7. I think deadline is over for this. And yeah. So after the question, after deadline, you can see this feedback here. Some details of the solution. So how that we are getting the answer. So
Okay, okay,
okay. So
okay.
for each question, this feedback is mentioned. Sometimes it is mentioned in the detail. Okay. So based on the questions like this, you can see for this question, each step by step it's mentioned how we are getting this. Okay, so you can just see this feedback. If you are not able to understand the feedback, then you can post on the forum and you can discuss in the session also. Yeah, Divyans.
Sir, there was this one question in week 6. In yesterday's session, it wasn't discussed. So this question was like on tree traversal on a full binary tree. Should I
Okay.
share it? Uh,
I'm opening that. Which question I have
uh,
opened the assignment?
Not the assignment one, sir. It was discussed in TA session.
Okay, okay, okay. So that is another. Okay, just 1 second. So do you
Sir,
want to share it?
yes, sir. This was the question, sir.
Consider the following tree traversal on a full binary tree. In order, which of the following traversal options are sufficient to uniquely reconstruct uh, the full binary tree? Okay, okay. So, so that topics here we are talking about the binary tree, not binary search tree. Okay. So
Yes,
in
sir.
binary search tree we have some order in the elements, but in
Mhm.
binary tree we cannot give any order in the based on the value.
Mhm.
So actually we need at least two pair. At least we need two pair, either in order and pre-order, okay,
Mhm.
or in order and post order.
Mhm.
Yeah, so these are the two we can uniquely reconstruct the tree, but also there is that pre-order and post order is also possible. But
Yes, sir.
in one case, actually, some tree our tree may be some different to the
Mhm.
original one.
So, sir, can you put an example where first and third option will be used? Like a C option will be correct in any
First and
tree?
third. Okay, okay,
Yes, sir.
okay, okay. So that is not discussed yesterday.
No, sir, it was given as like to practice.
Okay,
So
okay.
what will be the correct answer for this question?
ABC.
Okay.
Yeah, ABC is the answer, but C is also not
Yes,
100% because in some case our tree may be become different.
sir, it
Okay.
was like I searched online, so it was showing that it is for a specific
Hmm.
case.
Yes.
Yeah, but could not understand how they will
Okay. Okay.
make
That
the
I'll
tree.
explain. Okay. That I'll
Mhm.
explain.
Mhm.
Yes. Yeah. So we will discuss this when we will discuss the questions of week 6 today. Okay. At that time, I'll also discover this.
Okay, thank you, sir.
Okay. Yeah. Okay. Karthikeyan.
Today we will discuss only 5, 6, or we will
Yeah,
discuss
5, 6 only. Today 5, 6, and then next Friday 7, 8.
coming. Okay, okay.
Friday
Tomorrow, how
session.
about tomorrow?
Tomorrow is TA session, so TA is I think also planning to discuss week 7 and 8 in tomorrow session. So that session is actually going totally separate. Okay, so yeah, this instructor session actually we are discussing all that separately.
Okay.
Okay, so let's. Uh, okay, if any specific doubt in the mock questions, so shall we start from mock questions or from my questions? So I have also have 12 questions. So okay, then let's start from my question. Okay, after that we will discuss the mock question. So if you have any doubt in mock questions, so that you can also discuss. Okay, so maybe some questions will be similar, so that we will check. Okay, so yeah, this is the first question we have for the practice. Okay, but all these questions I have taken from the previous exam papers. Okay, and also this mock question is also not the new questions, that is also taken from the previous exam papers. So you can directly get the idea what type of questions will be there in the exam. Okay, so now this is the first question here. This is about the dynasty algorithm. So one graph is given, and this graph is directed graph, weighted graph, and we are running the dynasty algorithm on the vertex P. Okay.
Screen
So
visible, sir.
screen is not
So
visible.
screen is not visible.
Oh, my screen. Oh,
So the screen is
yeah.
not.
Actually, I
It
stopped
is
here.
not share. You start
One
sharing.
second. I hope now this is visible.
Yes, sir.
Okay. So I have a little bit zoom it. Okay. So now this is the first question. Here one graph is given. Okay, and this graph is directed and weighted graph, and we are applying the Dirichlet algorithm on this, and we are considering the start vertex is P. Okay, so this is given in the question statement. Now we are asking that what is the order of the vertex nodes in which the nodes are marked as visited by Dirichlet algorithm. Okay, so if you remember the algorithm, so you know that when we apply the Dirichlet algorithm, so we also consider one visited dictionary or maybe list, and during the process we mark that if we are visiting any vertex, we mark that as a we have visited and we mark as a true. And in the remaining process we always check that if the coming that adjacent vertex is visited or not visited. So based on that we decide that which next node we will visit in the further process. So that is one actually property, one part of the algorithms. So here, if you know the steps of algorithms, then you can remember that you can conceptually apply the Dirichlet algorithm on this graph and check in which order our nodes will be visited when we apply the Dirichlet algorithm on P. Okay, so if you know the conceptually, then no need to remember the code for this. You can directly apply the steps of the Dirichlet algorithm on this. So what is the how the Dirichlet algorithm works actually? So we can apply the dry run on this. So because starting vertex or source vertex is P, so that means for the initialization, okay. So for the initialization, we always initialize 0 vertex, 0 value distance for the source, and remaining infinite. Okay, so this is the first step we apply in the Dirichlet algorithms, and we also maintain one visited dictionary. So visited dictionary says how many total vertex we have. We have total 6 vertex. 1, 2, 3, 4, 5, 6 here. So P, Q, R, S, T, U. Okay. Initially all are false. Okay. So now when we are applying, so this is the source vertex. So this is the source vertex, and we are starting from this source vertex. So this vertex will be visited first. Okay, so that means we will mark this as a true as first. So you can see in the option we are getting all the first node P. So we cannot identify the option. So after that we check the distance. So where we can directly move from this P vertex. So we have two choice, 5 and 8. Okay, from P, because we have two direct adjacent which are directly connected to this. So that means from P to Q we can reach in with the weight 5. So and in the process, if we are getting smaller distance from the source to the previous distance, okay, what are the previous assigned distance or at that node, so then we will update the distance by the smaller one. Otherwise we will skip. So in this case, you can see P to Q, we are getting this is 5, which is smaller than the infinite previous assigned. So we will update by this 5. And next, similar to P to U. Okay, this is 8. So this will be updated by 8. So now these are the two. Now we have two nodes to visit it. So in the every iteration, we always check which vertex contain the minimum distance from the source. So now you can see P we have already visited. Q, U, this is also infinite. Okay, so Q, U, R, S, T all have some weights. So this is Q is 5, U is 8, R, S, T are infinite. So smaller one is the Q. Okay, so this is the smaller one. So that will be selected next to visit. Okay, so that means we will select this Q to visit next. So now the second is I'm writing here. So P next will be visited Q. Okay, now Q will be marked. Q will be marked 2 here. And when we are visiting this Q, now we will check from here. Okay, so Q to U. Okay, because U is still not visited, we always check the vertex which are not visited. Okay, so Q to U, because from P to Q is 5, then Q to U 5 plus 4. We will always consider the distance from the source. So 5 plus 4 is 9. 9 is greater than the previous distance 8. So this will not update. Okay. Same Q2 R. 5 plus 6 11. So 11 is the smaller one compared to the previous one. So 5 Q2S. So 5 plus 3 is 8. So this is also updated. 8. Okay. Now this is the next updation. After that, just check in the non-visited node which one have the smaller weight. Okay. So here 5 plus 3, 5 plus 4, okay, 8, infinite, and 11. Yeah. So here,
one question here. We are done with Q, right? P and Q are now done. So now we have to look at the nodes which we can reach from Q, like U or S, or we have to move to the next node. Say after Q, we have to look at the neighbors of Q, which has the lowest one. Like S.
not neighbors. All the remaining vertex which have the smallest weight, that we will select next.
So it can be anything, right? Let's say,
Yes.
for example, in this case, we have to go for S because it has the lowest weight. Let's say if Q to U is like 2, then we will have to choose U, correct?
Sorry, can you repeat? I just skipped.
Sorry, let me repeat myself. So now from P, we are going to Q, okay,
Yes.
because it is the lowest weight. From Q, we will have to go to S, that has the lowest weight, correct? Okay, from S, then we will have to go to R, right?
Why we are going from Q to S? Because now in the remaining part, okay, so these two are visited, P and Q are visited now, okay, and unvisited vertex are S, R, U, T, and out of these, we have the smaller weight on U and S, okay, U and S. But in question statement, this is also given that if we have two vertices have same distance, then algorithm picks the next vertex which comes first alphabetically. So S is coming alphabetically first compared to U. Okay, here weights are similar, but we will pick the small which alphabets come first in alphabets, so that we will select S. Okay, so because S comes first, so next will come S here to visit. So this node will be visited next. That's true. And after that, we will check the distance from S to all neighbors which are not visited. Okay, so S to R. So now S distance is 8. 8 plus 4, 12. 12 is greater than the previous distance, so we will not update this. And S to T is 5. And 8 plus 5 is 13, which is smaller than the infinite. So this will be updated by 13. Okay. Now just check what are the remaining weights on the unvisited vertex. Okay, so if anyone have any query, just open your mic and ask, because I am not able to see the.
Okay. Why are we actually going to S when the weight for S and U is the same, 8 and 8?
So this is given in the statement. You can see this line. Note: if two vertices have same distance, the algorithm picks the next vertex which comes first alphabetically. Okay. So because of that, we are selecting S. Otherwise, if this statement is not given, then we can select anyone according to the concept.
Okay.
So both will be correct. So here S is now the third. So you can see now the only two options are remaining for this. No, three options are remaining: A, B, and D. So now C is incorrect. And after that, next vertex is U, R, and T are remaining to visit. Okay, so which one have the minimum distance? U. Okay, so next definitely this will be select. So U will select, and from U, just look, we have 8 on U, and U to T is 6. So 8 plus 6, 14, which is greater than the previous one. So that will not update. Okay, and there is no outgoing edge from the U apart from this. So now this part is complete, and after that we will look next unvisited vertex. So this is R and T. R have the minimum 11. So that means R will be selected to the next visited vertex. So this is R, and from here you can see no nodes are connected which are not visited. So there's no steps remaining for this. Now we will select the next unvisited. So this is T. So this is the T. Okay. So in this manner, you can apply the dry run of the Dijkstra algorithms, and you can figure out that how the vertex will be visited. And in this
So I
manner,
have one question.
Mhm.
Here we have been given the arrows. So the arrows do not have any directional traversal.
Mhm.
Means
Okay, so
like we don't.
that is not that will not affect, because if the direction is not there, then you can traverse from Q to R and R to Q both side. Okay, so the meaning is
No, here we have got the directions from P to Q, Q to S, S to R, or S to T,
okay,
or R to U. So
yes,
we traverse from P to Q or P to U. But because P to U is 8 and P to Q is 5, we take P to Q. Then from Q, we have three arrows, one going to S, R, and U, wherein Q to S is the lowest weight. So we take P to S.
no, I think
That
you are
will,
not understanding correctly. We are not selecting from by the A edge. Okay, so Q to 3, we are not selecting based on this 3. We are simply updating the weight on the adjacent vertices first. After that, we are looking all unvisited vertex distance and which have the minimum distance. Okay, so from P to V, from P vertex, we can move to Q and U. Okay, only then we
yes,
are updating the distance of Q and U from P. So we have
yes,
updated this 5 and 8.
8.
So now next, we are not selecting Q because of this edge is minimum 5. We are selecting this. We are looking all the vertex weight. So I'm also just mentioning another table which we also maintain. So that is actually P, Q, R, S, T, U. Okay. So initially P is 0, all are the infinite. Okay.
Yes.
Okay. When we visited P, so now we updated Q is 5 and R is 8. Okay. And remaining are
No,
infinite.
R, no, U is 8.
Sorry, U is 8. Okay. So this is infinite. One second.
So, sir, can we say that we can calculate the first minimum weight of each the vertex and then sort them in the ascending order?
You can say that. So this is 8. Okay. Now what we are looking, we are checking all these remainings because now this time all are unvisited. Okay. So all these P, Q, R, S, T, U unvisited. So which one have the minimum distance? 5.
5.
Because of that, we are selecting this Q. Okay.
Okay.
Not from the edge. So we will always look all the vertex which are not visited and we will check their weights, and then we will select the minimum one. Which vertex have the minimum one? Okay.
Yes.
So this is the first step. So then we will find out this is the 5. Q is the next smallest one. So we will select this Q, and from Q we are updating the vertex of the all adjacent of Q. So
Yes.
Q to U. So 5 plus 4, 9, but you have 8. So we will not update
8.
this. Okay. So Q to R, 5 plus 6, 11. So this is
11.
updated. Okay. And Q to S, this is 3. So 5 plus 3, 8. So now this is also updated. So that means when we are selecting Q, now weights are updated like this. So U is still 8 and R is become now 11 and S become 8. And this is still infinite. Okay. So we will check the smallest one among all the unvisited vertex in this.
Plus the alphabetic.
Then, so we are finding out 2, 8 and 8. Now we will select the alphabets
Alphabetically
earlier
smaller.
one. Yeah, smaller. So this
So S is the next one.
S1 is the next one. Okay. So that means this is now selected S. Now we are updating the weights again. So our S2T, this become 13 this time, and that will remain 11. So R will remain 11, and that U will also remain 8. Okay. Now these 3 are remaining. Okay. So this R, T, U, and out of these, you have the minimum.
R is the smallest. No, U is the
U
smallest.
is the smallest. So this U will be selected next. Okay. Like this. Okay. Then we will update the distance. So u to t is 8 plus 6, 14. So this is again greater than. So no update is happening. So we are remaining now 11 and 13.
13.
So which one is the smallest? 11.
R.
Okay, R. So R will be selected next. Now there is no update from the R. So then we will select the last one. So this is the remaining. So this will be remaining 13. So this is the order, how we are visiting the vertex and how we are getting the shortest distance also. Okay, so finally we are also getting the shortest distance. So you can see if P finally we get 0. So Q, the shortest distance is 5. This is 8. This is 13. This is also representing the distance from P for each node. So this is the solution. Actually, we are finding out from the shortest distance from the source to each node. So in this manner, question may be asked. So maybe some graph is given, the shortest distance is asked to the another vertex, the order of the visited vertex.
So I have one more question. When do we take into consideration the arrows?
Consideration of the arrow. So here arrow is representing of the direction where you can move. So here Q to U, this direction is arrow is given. That means you can only move from Q to U, not U to Q. Okay. So here, what are the adjacent of Q where you can move? So adjacent of Q is now U and R and S, where you can move. But if you look from the U, so you can only move to T. Based on the direction, you can only move.
Here we do not have to visit all the nodes. It is not necessary to visit all the nodes, right?
So actually our goal is to find out the shortest distance for each nodes from the source, but there is a chance if you are not able to reach because of the direction. So maybe if any vertex are not connected properly from the source, so there is no path from to reach. Suppose if we connect this T like in the reverse edge in the both direction, then you cannot reach to T from P. Okay, so you cannot reach to T, and then shortest distance will remain infinite for this T. Okay, but if direction is not given, then that means if Q and U is connected without any direction, so that means you can traverse from Q to U and U to Q, both direction.
So, but then in that case, we can directly come from P to T via R and S.
But
so 5 plus 3 plus 5. So that comes to 13, which is the answer.
No.
And we can even check P to U to T, because that is the other direction in which you can travel. So that comes to 14. So between 13 and 14, 13 is the shortest distance.
So but this is the small graph. But suppose the graph is given, there are maybe 100 way to reach at that node. So how you will figure out this? Okay. So we are properly applying the algorithm so to find out the steps. Okay. So that is actually maintaining all these things. Which one is the shortest? Okay. So this is first question. Okay, now move to the second. So any query in this? Any doubt?
No problem, sir. Thank you.
Okay. Now second is this question. Which of the following statement is true about digestion algorithm to find shortest path? So this is conceptual theoretical question.
Is the session being recorded, or would you be able to share this presentations at the end of it?
Yes, session is also recorded and it is live streamed on the YouTube, and we will also share. Okay, so on the calendar event we will share the drive link.
Thank you.
E is true.
Which one? Sorry.
E
is true. E is true.
E is true.
A is true.
D is also true.
D is also true. And yeah, P is also true. C is false.
Okay, C is false.
Sir, A is false because it works with the negative weights.
No, it doesn't work with negative weights.
B is false.
The B is also false.
The B is false.
No, B is false.
How
And
can B be
someone is
false?
also mentioned A is false.
Oh
No,
no,
A
not
is
it
right.
does not give for all pair of
It
nodes.
doesn't work for negative weights.
One second.
The extra doesn't work for negative weights.
Okay, so just
false. B and C are false. The rest are true.
B and C are false. Okay. Okay, let's just discuss one by one. So A step, that A option, Dijkstra algorithm doesn't work for graph with negative weights. So this statement is actually is a
Sir, may.
This will be always
It may work sometime.
It may work.
Yes, sir. But with negative cycle, it doesn't work. But with negative edges,
may
it works.
It doesn't work for negative weights.
Dijkstra algorithm doesn't work for graph with negative weights.
It should not have a cycle. Cycle only it will not work.
For negative
Cycle should not be
weight,
negative,
okay.
but negative weights are fine.
Both cycle and negative weights it should not
Negative
work.
weights are not always fine, but sometimes it will work, sometimes it will fail. So it's
For
not
negative weights.
for negative weights, sometimes it will work.
Yeah. So in negative weights, overall we just give this statement Dijkstra algorithm not works for that negative weights. Okay. Why we are giving this statement? Because it may be fail for the negative weights. So we have to check the condition when the Dijkstra algorithm will work. We have to also check this our solution is correct or not. But sometimes it may work. What is the condition? I think one question is based on this is inside the mock. So where let me just share that question also. When the Dijkstra algorithm work actually. So yeah, this question, okay. So here the same Dijkstra algorithm we are applying on the S, and here negative weights are there, okay. But still you will get the correct answer for all the remaining vertex if you apply the Dijkstra algorithm on this graph. So why? Because here the weights, this negative weights we have on the edge, which are actually going from the visited vertex to unvisited vertex. So that will not affect. That will not affect the output. But if some case in the process, if any negative weights are coming from the visited vertex to visited vertex, or maybe unvisited vertex to visited vertex, like this. Okay, if any vertex which we have already visited before, and any edge is coming from any other unvisited vertex to that node,
Exactly.
so that will actually impact, that will reduce the weight which we have already traversed, and we will not we will never look that node, which because we have already visited that node.
We have decided based on the minimum. At that
So
time it was
negative
minimum.
cycles would be an apt way of putting it, or
No, this is not regarding the cycle. Here there is no cycle. Okay.
So can you
yeah,
please
that's what I
explain
mean.
this
There is
point
no
a bit
negative
again?
cycle. Like if you go through the cycle, it does not reduce. Is that the reason why it will work?
No.
No.
Okay.
That is not the issue. So let me just give one example.
No, but then, sir, what are we supposed to consider?
1 second.
Because according to the notes which are given, it says that it can only be used on graphs with non-negative edge weights. If
Because
the
of that,
graph contains negative weights, Bellman-Ford algorithm is a better choice. It
Yes.
says like that.
Is a
So,
better choice.
It is a better choice. But then in conceptual question, when this type of a question is asked, what are we supposed to consider?
so because of that, I'm explaining this. This condition is mentioned that Dijkstra algorithm doesn't work on the negative bits. So this is not exact correct. It may works. Okay.
So this statement is ambiguous.
No, it's not 100% true.
That is what I'm saying. It's ambiguous. Means it may be true, it may not be true. So,
but So in general, actually, if our algorithm is not working in some certain case,
Then it
so
is false.
we cannot
No, but then
use that algorithms on the work.
when a conceptual question is asked,
Huh.
a concept says this way or that way. You cannot have a middle path.
So if it is
So
has been asked,
because of that, this statement is generally considered as a Dijkstra algorithm doesn't work on the negative weights.
Yes, that is what I
Generally.
was asking. Whether if it is a conceptual question, we should answer it as it does
Yes.
not work on negative weights.
Yes, correct. So for this question, actually, this option is correct. But for the particular question, so like this question in the mock, okay, this question is a mock. So here one graph is given, and we are asking that Dijkstra algorithm will return the correct output for this or not. So here actually you have to check. So here actually Dijkstra algorithms is returning the correct output. So like I'm giving the example in which case actually this Dijkstra algorithm fails and which case not fails. So like suppose if we have a graph like this and our weights is like this, so like this is 4 and this is 2 and this is minus like 3. Okay. Now if you start the Dijkstra algorithm on A, then you will traverse this A first. After that you will update so this is infinite and this is infinite. So now from A this is 0. So A to B, now it become a 4 and A to C become a 2. Okay. Now you will select the node C for the next visited. Okay. So now you are checking from this side. Now you will check there's no edge going from this C to B, so that will not update. So there is no effect. Okay. But after that, now we have visited this C and A. Now we will check from the B. Now from B, we have one edge which have the negative weights -3, but we cannot look this because this is already visited. We will not update this because we have already visited C. So that we will not, according to the algorithm, we will not check for this. But if you check this in the diagram, so A to 4, B is 4 and B to C is 4 minus 3 it become a 1. So that means distance from A to C should be 1 in the as a correct answer, but we are getting 2 by 2.
Yes.
So here we are this is not a negative weight cycle like this, and this is not a cycle. But what happening actually, we are getting this negative edge from the unvisited vertex which is not visited yet, and we are just going to visit this B, and this edge is going to the already visited vertex. So that is actually a problematic for Dijkstra algorithms.
Sir, for this type of question, first we have to run the Dijkstra algorithm and accordingly check the condition for this incoming edge. On the
So if you know this, I have just to conclude this. If any edge is going from the unvisited vertex to already visited vertex, and that contains the negative weights, so that will be actually will return the incorrect output according to the Dijkstra algorithms.
Can you just repeat the statement that you said at last?
So here actually we have visited A and then C. Now we are going to visit B. This is not visited yet, but from B we are looking. So this B is not visited, but there is one edge is going outside from this B to already visited vertex, and that contains the negative weights. So that means there is a chance to reduce the distance from B to that vertex which we have already visited before.
Yes, sir. Got it.
Due to this negative distance. So that actually in this case we will get the incorrect output. But suppose if we reverse this thing, so that will not be problematic. Suppose if this edge is going like this. Okay, so now this will be updated from this C also, because we will just check this. So this is suppose -3. So 2 is C. Now we are selecting C. So from C, 2 minus 3 is become -1. And when we will look from A, this B, so now there is no updation. Okay, so this is now correct. So A to C is 2, A to B is -1. Because this time, this edge is going outside from the current visited node to the unvisited vertex. Okay, so that will give the correct answer. So in this mock questions, actually, all edge which have the negative weights are actually going from the source vertex, which is actually we are visited first, and all edge are going to the unvisited vertex.
So, sir, in short, if a visited vertex weight gets updated due to the negative change, so the algorithm won't work on it. Okay.
Okay.
And sir, if you are starting from some vertex and during visiting, if it is the graph is getting some cyclic, then we can say that this will not deliver the desired result actually.
So cycle case we have also checked the negative things here. If we have the cycle and if we have the negative weight cycles, suppose so that we have to check our cycle is the negative weight cycle or not.
If the cycle is negative, then it will not deliver the
definitely it will
result.
not work.
If the still the during this traversing from one node to one vertex to another, if the graph is not becoming cyclic, then it will deliver the desired result, na?
No, not in the Dijkstra algorithm case. This is not a cyclic, na?
Will the extra work for positive cycle too?
Yeah, work.
Okay.
Dijkstra algorithms works correctly with the positive weights. So either graph contains cycles or not. Okay, so it always works. But negative weight cycle, it doesn't work. Negative weights also we conceptually say that it doesn't algorithm doesn't work. Okay, because when it will work or when it will not work, we cannot always check according to the Dijkstra algorithms. We are directly applying the algorithms on the some graph. So if that contains the negative weight, so there is a chance it become fail.
Yes.
So we cannot use on this type of graph. So conceptually, Dijkstra algorithm doesn't work. Okay. But for the particular question, we can say that so like this question, for the correct answer is Dijkstra algorithm will return the correct answer. But apart from that, Bellman-Ford algorithms will work on the negative weights, but not negative weight cycle. Similarly, Floyd-Barsel algorithm is also work on the negative weights, but not negative weight cycles. So okay. So next statement. So this is actually true conceptually. So it returns the shortest path between all pair of nodes. So Dijkstra algorithms is not designed in this manner. So this returns the shortest path from one vertex to all other vertex, not all pair. Okay, so this is not correct. The shortest path returned by Dijkstra algorithm always passes through the least number of vertices. This is also not true. Okay, so suppose we have like this A vertex and this is like D vertex, and we have distance like a B, C.
Actually, we visit all the vertices.
So and one edge is connected like this. Okay. So here I suppose 5 paths like 2, 1, 3, and this is a greater value 6. Okay. So shortest path written by the Dijkstra algorithm always passes through the least number of vertex. So this is not guaranteed. So number of vertex may be greater. So this is also false. And to decide which node is visited next, Dijkstra algorithm select the node with smallest known distance. This is true because we have already we have already done this. So if you are getting smaller distance, then we update the distance. Okay. So this step is true. It can find the shortest path from only a cyclic graph. So this is also not true. Okay. So only option A, and this is also D. AD is correct. All remaining are false.
So cyclic graphs also it can actually figure out. That's okay.
No, cyclic graph.
Positive cycle.
So here it is not mentioned that it can find the shortest path for. One second. It can find the short. Oh, this is true. Okay. Only a cyclic. Okay, no, not true.
Not true. Only a cyclic, not necessary.
Can you explain why option D is incorrect here?
No, D option is correct.
D is correct.
Okay, D is correct and A is correct. B, C, E is incorrect.
Can you explain B once again, please?
B.
B as in Bombay.
C option, sir.
This one?
Yeah.
And C.
So we have two categories of the shortest algorithm. One is single source shortest path, and another category is all pair shortest path. So all pair means when we are applying the shortest path algorithm, we will get, suppose we have four vertex in the graph. So A, B, C, and D. So finally, we will get the distance between every pair. So if we can look the shortest distance between B and C, C and D, D and A. So that means our algorithm will return the shortest distance between every possible pair in our vertex. Or if our algorithm is applying on the source vertex and it is returning the shortest distance from the source vertex to all other vertex. So that is different category. So Dijkstra algorithm and Bellman-Ford algorithms are single source shortest path. So single source means we are giving one source and we are finding out the shortest distance for all other vertex from the source. Okay, but Floyd-Warshall algorithms actually is a all pair shortest path. So in that algorithms, we finally get a matrix type of output. So where the vertex is giving like this, so A, B, C, D, and similar A, B, C, D. And for each cross value is actually represent the distance between row and column value. Okay, so like B to C. So that shortest distance will come at this place. So that will be the all pair shortest path. So finally we will get the all pair shortest distance using the Floyd-Warshall algorithm. So that Dijkstra and Bellman comes under the single source shortest path. Okay. Shall we move?
Yes, sir.
So this algorithm is regarding this Floyd-Warshall algorithms.
Yes, sorry. One point I was just noting down. You were mentioning Dijkstra earlier. You were just mentioned Dijkstra does not work with negative weights. Bellman-Ford works with negative weights, but not with negative cycles. Along with that, you said there's one more which works with negative weights, but not with negative cycles. That's Floyd-Warshall, right? Yeah. Thank you.
Yes.
Thank you.
So this question is regarding Floyd-Warshall algorithms. So yeah, which statement is true about the Floyd-Warshall algorithms? So if you know the conceptually that Floyd-Warshall algorithm
First one is correct.
It can detect negative weights, yes.
Can you just tell me the answer? How we can detect the negative weight cycle?
Like after n-1 relaxation, if you do
n-1, why we are not using n-1 things in the Floyd-Warshall. This is Floyd-Warshall algorithm, not Bellman-Ford. So how you can identify that graph had negative weight cycles?
The update reduces the weight.
No change in the weight after a few cycles, like 2 or 3.
No.
If the distance changes after n iterations.
After n iteration, if it still reduce the distance, then
sir, it will run infinite times, I guess.
No, algorithms will run perfectly. But actually, if you remember the algorithms of this Floyd-Warshall algorithm, so let me just open this. Bellman-Ford.
After n iteration, it still reduce the step, then it's cycles.
So you can see in output, actually, we get this type of matrix. Okay, so this type of matrix. So actually, this is returning each pair. Okay, so this is a pair. Wise we are getting the shortest distance, all pair shortest path. So suppose in matrix, if we have this type of matrix like A, B, C, and D, and same here A, B, C, and D. So in cross, we are calculating the all distance from A to B, A to C, A to D, all this place. But we are also calculating the distance from A to A. Okay, and what is the definition of negative weight cycle is if we add all the cycle path weights, we will get the negative value. Suppose we are starting from A and we are going to B, and then we are going to C, and then we are coming to A. So if this cycle is a negative weight cycle, so the A to A distance should become less than 0 or in the negative forms. Okay. So in final output, if this is not coming 0, if you're getting at any A to A or B to B or C to C or D to D, any place if you're getting negative value, so that means that graph contains the negative weight cycle.
So basically the diagonals, you mean?
Diagonals. The diagonal value, if you are getting any diagonal value negative, that means graph contains the negative weight cycle. So this is the identification of negative weight cycles in the final output. Okay, so we can detect this. So this is true. Now the time complexity of float Warshall algorithm is V square. So where V is the number of vertices. Is this true?
No, sir.
No.
No.
It's with
Actually, Q. So we run 3 nested loop. One for the number of times, one number of matrix actually we calculate. Suppose we have the 4 vertices. So we have to calculate it 2-dimensional matrix 4 times. Okay, so we use 3 nested loop here, so our complexity will become VQ. This is not correct. It works correctly if the graph has negative weight as weights, but does not have negative weight cycles. So this is true. Okay. If graph have negative weights but does not have negative weight cycles, so it will work correctly. So this is true. This is true. Now the formula to compute the shortest path from vertex I to J in float Warshall algorithm. So this is the single formula which we used to calculate the distance in our matrix. So that is actually, suppose we are looking, we have graph like this. So A to B and B to C. And, so in every time we always, suppose we are checking from distance A to C. So we always check if our direct distance, okay, so direct distance from A to C, what distance we have, and the distance from any another vertex. So what we are considering, okay, so A to B, then B to C. So we compare the both distance and we pick the minimum one. One direct distance A to C and one another is through the node. Which one is the minimum? So suppose we can say that if you are looking from this is I and this is J, okay. So first we will look from I to J directly, and another we will check I to, suppose this is K. So I to K and then K to J. So which one is the minimum we will pick for the distance. So we use this formula. So in this formula you can see SPK I comma J. So this we are calculating. So this is K, this is representing the matrix number. So what current matrix, what vertex actually we are selecting for the checking the path. Okay, so here suppose this K is represent the number of, suppose this time we are looking through the B. So this K value will be represent the index of this B. So every time we will just check the direct path and through the K path. So here this is the minimum one from the previous result. From the previous result, we will directly pick SPK minus 1 I comma J plus SPK minus I comma K. Okay, and this is KJ. So this formula is not correct because the formula should be one side our SP K minus 1 and this I to K. I to J, sorry. I to J
directly.
Directly. Comma, another side is SP K minus 1 and I to K, then plus, okay, SP K minus 1 and J, that K to J, K comma J. Then we will pick the minimum. So this should be the correct formula. So here this is not the correct one. So this D is the incorrect. Okay. So now move to the next. Consider the following adjacency matrix, the directed graph with 5 vertices. And what is the cost of the minimum spanning tree for the given adjacency matrix of a graph? So now this question is based on the spanning tree. And spanning tree, we have two algorithms, Prim's algorithms and Kruskal algorithms. So for this type of graph where you need to find out the cost, so instead of Prim's algorithm, just use the Kruskal algorithms. Okay,
Yes, sir.
that Kruskal algorithm is better. Just here, how many nodes we have? So we have total 5 vertex. So like we can give the name like 0, 1, 2, 3, 4, 5. Okay, so like this. First thing, you can create a graph using this matrix because it will create some confusion to select the edge. Okay, or you need to only, so this is actually undirected graph. Okay, so just look the value only this part, the above one, because all the lower one is just a repeated direction. Okay, so this is 0, this is 1, 2, 3, 4, and 0, 1, 2, 3, 4. Now you can create a graph directly. So 0 to 1 is
0, 1.
So 0 to 1 we have 1, and 0 to 2 we have.
We can also connect
8.
3, 0 with 1 weight.
So 0 to 3 with 1. So I'm creating a complete graph first.
Actually, sir, without creating the complete graph, prims, we can directly utilize prims, na? We pick up the shortest ones.
But you have to think about the completely, and maybe you just pick any wrong value from the direct matrix.
So we will start from the minimum one, na? Like in the graph matrix, we can see 1 edge, 3 edge, 2 edge, minimum ones. So
that you can also do. Yeah, that we can also do. So out of these, always select the smaller one first.
Minimum ones, yes, and we have to only avoid the cycle only.
You have total 5 vertices. That means in spanning tree you will get only 4 edge.
Yes.
Okay. So yeah, that is also correct. So just pick this smaller one. So 0 to 1, that will be a part of the spanning tree. Yes. After that, next smaller is 0 to 3.
0 to 3.
Okay. So let me just remove this. So 0 to 3 is, this is also 1. So you can connect. And next smaller is this.
2, 4, 3.
Okay. So 3 to 4. 3 to 4 is now 2. And next smaller is
4 to 2. 4 to 2 with 3.
So this one.
Yes.
Okay, so 2 to 4. So 2 to 4. Yeah.
Yes.
After that, there is no possibility because you got the 4 connection. Okay. After that, if you take anyone, so it will create a cycle. The total distance is 1, 2, and this 0 to 3 was 1. Okay, so this was 1. So 1 plus 1, 2 plus 4 and 7. So answer is 7 for this.
Yes.
Sir, can you please explain how you make the graph? Like this prism.
No, I am not using Prim's algorithms. I'm directly picking the smaller one. I'm applying the Kruskal algorithm here. So this is an undirected graph. Okay, so you can only look only the diagonal upper value because the lower value is just a reverse direction. So 0 to 1, lower one is the 1 to 0. Okay, so only look the above one value. So here you have 5 vertices. So 0, 1, 2, 3, and 4. Like this time I'm creating this. After that, this is totally disjoint. Now I'm picking the lowest weight. Okay, so this, you can see this is the 1. We have the lowest one. This is connecting 0 to 1. So when we connect this 0 to 1, it is not creating a cycle. So we can pick. Okay, now this is selected. Now next smallest one. So we are applying the Kruskal algorithm here. Okay, so Kruskal algorithm works like similarly. We always pick the edge which have the smallest weight if it is not creating cycle. Okay, so 0 to 3. So 0 to 3 is now connection is like this. Okay, this is and next smallest is this 2 in the remaining part. So this is 3 to 4. So 3 to 4 is now 2, and next smallest one is 3. 2 to 4. So 2 to 4 is now 3. So now all vertex have now connected. Okay, if you connect any edge in between, that will create a cycle. So you can stop the process because in 5 vertices you need only 4 edges to connect. Okay, so 1 plus 1, 2 plus 2, 4 plus 3, 7. So total cost is 7. This is the minimum spanning tree. Okay. So another type of questions is maybe also asked. So like in the mock question. One second. Mock question is also not given. Okay. So what are the other type of is possible question for this minimum spanning tree is? So maybe some graph is given like this. Okay. So this graph is given suppose, and we are finding out that apply the Prim's algorithm on this and find out the visited order like this algorithm we found. Okay. So similar manner, and you can apply the Prim's algorithms and you can figure out that how the vertices will visited in the Prim's algorithms. So that is also one possible question. And edge selection. So in if you apply the Kruskal algorithms, which edge will be selected? What will be the order of edge selection? That is also one possible question. Okay. So you should know the conceptually Prim's and Kruskal algorithm, or then you can apply the algorithms. Otherwise, if the question is asking just a minimum cost, directly applying the minimum that Kruskal algorithm. So that is actually easy to apply.
So for the sequence, we will need Prim's.
For sequence, the visited vertex sequence, you need Prim's algorithms. So actually, Prim's algorithms is very similar to the Dijkstra algorithms, but we always update the weights from the current only from the current vertices which we are just looking for. Okay, not from the always source.
Actually, they will mention, sir, na? Like they need the sequence from Prim's. Like
yes, that will be mentioned in the question.
From Prim's they want. Yes.
Okay, suppose if you are applying the Prim's algorithm, what will be the visited order of vertex? Yes. So like this, it will be mentioned. Otherwise, some conceptual question you have already seen in the mock, so that we will also discuss. So like one is possible question is here. So question number 5, you can see. Suppose we run Prim's algorithm and Kruskal algorithm on a graph G which have edge with distinct weight, and these two algorithms produce minimum cost spanning tree TP and TK. Okay, TP means Prim's and TK means Kruskal. So these are the tree with total minimum cost CP and CK. Which of the following is true?
Trees will not necessarily always be same, but cost will always be same.
But I think you just ignored this question, this condition.
All weights are distinct. Then, sir, option C then will be the answer.
Okay, distinct weights. So no possibility for getting the same tree. Like
okay, here this is mentioned distinct weights. So you will always get a unique MST. Okay, if you apply the Kruskal or Prim's, you will always get the same cost and same tree.
Yes.
But if this is not given, then you will get the same cost but maybe different.
Then multiple tree could be possible.
Okay. So here this answer is the TPT are always the same and CP is always equal to the CK. Yeah, option C.
Yes.
Okay. So next one is this. This is also a very related to the. Sorry.
Can you explain the previous question again?
So here distinct weights are given, okay, in the graph, like we have connected A, B, C, D, like this, okay. All weights are like distinct. So 1, 2, 3, like 4, 5, like this, okay, and maybe 6. So in this situation, in final minimum spanning tree, you will always get the smallest one. That you will always pick the smallest weight edge first. So like here you will get A, B, C, D. So no edge are actually duplicates. So you always pick the smallest one. So A to B, then next smallest one, B to D, and next smallest one, if it is not creating a cycle, so that D to C, yeah, it is not creating a cycle. So like C. So 1, 2, and 3 are coming. So if you apply the Prim's or Kruskal algorithm, you will always get the same tree. because there is no duplication here, so that means Kruskal and Prince both will select the same edge, then same with the same cost. Okay, then you will get the this similarly. So this TP with tree. Okay, so tree of Prince and tree of Kruskal will be same, and this cost and cost is also same by the Prince and Kruskal. Okay, because our weights are distinct. If our weights are not distinct, then Prince and Kruskal will return the same minimum cost, but maybe different tree.
Understood, sir.
If 2 is like present in the 5 like A to C, then it will give different tree,
Yeah.
right?
Yes. If any weights are duplicates, like we have 1, 2, and so here suppose this is also 3. Okay, then two possibility are there. So A to B, B to D, and D to C. Another algorithm is pick like A to B, B to D, and A to C. So cost will remain same, but T now become different.
Sorry, which one is Prince in this? The first one, is it?
No. So
you just did it for Kruskal, right?
No, the question statement, it is mentioned that this TP is representing the tree of Prims. This is TK is tree of Kruskal, and CP cost of Prims and cost of Kruskals. So that means we are applying both algorithm on this type of situation. So our tree will be same or cost will be same. So that is actually asking the option.
Yeah, that is clear. The tree that you have constructed is through Kruskal, right?
Yeah, that I've just mentioned that if this weights is repeated duplicates, so like A to C and C to D is duplicates, then two different spanning tree are possible, minimum spanning tree are possible with same weight.
Okay.
That I mentioned. Okay, so maybe Kruskal will return another one and Prims will return a different one, but cost will remain same. Okay.
Okay, maybe I will ask my question towards the end of the class, if that's okay. Yeah.
Okay. No problem. Yeah. So next is also related to the Kruskal's algorithms. So just read this statement. Consider the following algorithms on a connected weighted graph with n vertices and m edges. So these are the steps actually. Okay. Sort the edge as E1, E2, E3 in decreasing order of their weights. Okay. So the weights are decreasing order. Now we are picking, consider each edge in sorted order. So suppose we are getting like 5, 4, 3, 2, 1, this weights. Okay, this is decreasing. Now we are picking the edge with the highest weight from the left to right side. If this edge is a part of cycle, then we deleted it, and we are running. We are performing this operation in the original graph. Okay, so like if our graph is connected like this, A, B, C, and D. Okay, and weights are like this. So like 1, 2, 3, 4, 4, 5, and 6. Okay, so now here weights are 6, 5, 4, 3, 2, and 1. Okay, after that we are picking the highest weight, the 6, and if this is a part of the cycle, any cycle of the graph, okay, then we will delete it in the original graph. So here we are deleting, we are not constructing minimum spanning tree, we are deleting the edge from the original tree, and finally we will get the spanning tree. So this 6, you can see this 6 vertex C to B is actually a part of the cycle, like this A, C, B, A. Okay, so we will remove this. Now
there are many cycles here. Why 6? Is it because of the highest weight, or
we are just selecting the edge in the decreasing order because we have sorted the edge first in the first step. Okay, and after that we are picking each edge one by one, and we are looking in the graph. If it is a part of the cycle, we will remove it. Okay, now this 6 is picked, now next 5 will be picked. So 5 is still a part of the cycle. Okay, so you can consider any cycle like A, D, B, A, or A, D, C, A, any cycle. So this will also be removed. Now next is 4. So 4, you can see 4 is also a part of cycle. Okay, so A to C, A, B, C, D, complete cycle like this. So this will also remove. After that 3, yeah, 3 is not a part of cycle now, 2 is not a part of cycle, and 1 is also not a part of cycle. So now the remaining graph is actually a minimum spanning tree. Okay, so this algorithm is working in this manner. Now the question is asked like this. So after performing this algorithms, what we are getting? So here exactly m minus n plus 1 edge will be deleted. So what is m? M is actually a number of edges, or n is representing number of vertices. Okay, and plus 1. So how many edges will remain?
M minus n plus 1.
N minus 1.
No,
N minus 1 will
if,
remain.
Just tell me in the terms of n.
N minus 1.
N minus 1 will remain.
N minus 1 will remain.
Yes.
So the remaining edge will be deleted. So just like this, m minus what are the n? So it will become a m minus n plus 1.
N plus 1.
Okay, so this number of edge will be deleted. So this is correct?
True, yes, sir.
Okay, at most n minus 1 edge will be deleted. So is this true?
No, sir.
No. No, this is not true. So after processing all m edge, the resulting graph is now connected. Yeah, this is true because we are getting the MST.
Connected.
So this is true. What remains at the end is a minimum cost spanning tree. This is also true.
सर जैसे डिक्रीजिंग ऑर्डर में था हमारे पास, तो एमएसटी में तो हमारे पास वेट छोटे वाले को पहले उठाते तब जाके सही बनता ना.
How, so we are just performing the reverse order, but this time we are removing the edge from the original graph.
Oh,
okay.
Like,
from the original graph. This algorithm is just a reverse.
Okay, we are directly eliminating from the original graph that those bigger edges. Okay.
So if any edge is part of the cycle, then we will remove.
Okay.
So we are doing the same process in the reverse manner.
Yes.
So this is also true. After processing all m edges, the resulting graph has exactly n minus 1 edge. So this is also correct. Okay, we have already seen this. So this is also true. So only B is incorrect.
So why B is incorrect? Because here we have only 3 edges and total vertices is 4. So 4 minus 1 will be 3, no?
They are saying to deleted. And
no, at most maximum. So this is the condition of maximum things.
Oh.
Okay, at most n minus 1 edge will be deleted. So what are the maximum number of edges possible in this?
N minus 1.
6.
6.
1, 2, 3, 4, 5, 6. 6. 6 edges were there. No?
So see, this is n minus.
Remaining. 3 are remaining.
3 will be deleted.
Sir, if we have n minus 1 edges in the spanning tree, and तो हम n minus 1 डिलीट ही कर सकेंगे वहाँ, तो स्पैनिंग ट्री बनेगी नहीं ना. n minus 1 तो चाहिए ही वहाँ पे स्पैनिंग ट्री में.
So for this example, actually 4 example, actually we are removing the same. Okay, so suppose if this is a graph. Okay, so we are removing the total 4 minus 1 3. But in the other case, like suppose we have 5. Okay, so 1, 2, 3, 4, 5. Now for 5 case, how many edges are possible maximum? 5.
Maximum deleting or
no, total number of edges possible for the 5 vertices.
So
15.
Like
15.
Each one with connected everyone.
So 5 into
15 edges, sir.
Everyone will have 4 options. So
1 second, 4 into
yes.
No, yeah, 5 into 4 divided by 2. So this
Divided
is
by 2.
10. Total 10.
10.
10 are possible. Yeah, in this case, so suppose for 5 vertices we need total 4 edge to connect in the MST, correct? So that means we have to remove 6.
6.
Okay, so this is not the n minus 1. this is now becoming n plus 1. So because n equal to 5 and n minus 1 is become 4. So this is 6. So this is not true always.
So what if we have only 8 edges?
Only
8 edges and it is still connected.
8 edges. No, this statement is regarding the at most n minus 1 edge will be deleted. So we are looking the worst case. What is the maximum possible edge deleted edge? Okay. So here maximum for the 5 vertices graph, we can remove total 6 edge. This is the maximum. But according to the statement, this 4 should be the maximum. So this is not correct.
Sir, what about option A?
Option A.
Yes, sir.
So option A is correct. What is the wrong in this?
No, sir, I'm talking about, let's say, assume we have only 8 edges and it is still connected. Then
How you can connect 8 edges in 4 vertices? Because maximum possibility only for 4 vertices is 6. So you cannot assume anything. How we are getting this formula correct? Because this m is representing total number of edges in the graph. Okay, so it may be anything, but n vertices is also given, and after in MST we always get the final number of edges n minus 1. Okay, if number of vertices are 4, that means that will be connected by the 3 edge at maximum. Sorry, at least. So if we have the 5 vertices, that means 4 edges required at least to connect all 5. So that is, we can say n minus 1. So these are the required number of edges to connect all the vertices. But total number of edges are there m. So that means we have to remove m minus this value from the graph. Okay.
It is asked like at most n minus edge will remain. It will be okay. Na?
At most. So this is the last option, na? So the resulting graph exactly n minus 1 edge.
For spanning, we need exactly n minus 1, not at most.
Okay, so after deleting, that means finally spanning tree will always contain the number of edge is equal to number of vertices minus 1. So we are getting this m minus n minus 1, so we can write like this m minus n plus 1. So if you take any value of m which is possible for this n, okay, so suppose you can maximum you can take 6, okay, but you have to remove 3. So this is representing the n minus 1. So 4 minus 1, 4 number of vertices minus 1, 3. So that means 6 minus 3, you have to remove maximum 3 edges. This is the maximum possibility for 4 vertices. Okay.
Yes, sir.
Yes.
Okay. Okay. So now this is the MST question. So let me just check the this mock question also. So I think you can find this question. Here we are asking the number of MST possible for this graph. First question of the mock. Okay, so in this graph you can simply take the vertices a1, 2, 3, 4 and 5 and 6. Okay, after that just look the smaller one. You can apply the Kruskal algorithms. So definitely here some weights are duplicates, but we cannot figure out that how many weights are possible by just looking this. So we have to create the MST first. So first we will pick 3. So that if this is the smallest one, definitely it will come in the MST. Okay, so because we need at least total vertex we have 6, so we need at least 5 edge. So 5 smallest should be come in the MST according to the MST definition. So 2, 3, 2 5, sorry, 2 to 5, this is definitely come in the MST. Now next smallest one, so next smallest one is the 3 to 6, so this is also come in the every MST. So this is the next, sorry, this is 4.
So can the it may have like if a n vertices, it may have more like more than n minus 1 edges in minimum spanning tree. Is it possible?
No, 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 no. Then it will come
Exactly
as
n minus 1.
n minus 1. If any edge, if you connect it after that, definitely it will create a cycle.
So it is giving only one MST unique.
So now we are selecting the next smallest one. Now third smallest one, you can see we have 3 place. Okay, so one for 3 to 2, second for 3 to 4, and one is 1 to 4. So all are actually connecting to the different vertices. So 3 to 2, which is so this 3 to 2, okay, and one is 1 to 4, and one is 3 to 5. So suppose if we start connected, which is not actually connected to any vertices, like this 1 to 4, this will connect. Okay, this 5 vertices, and if we connect 3 to 4, it is also not creating a cycle. This is the 5, and after that, still you can see this part is disconnected to the remaining part, and there is an edge which is connecting with this part 5. So this is the smallest one. So this is 5. Now our all vertices are connected. Now there is no another way to connect to all these vertices with the same total distance. Okay, so 3 plus 4, 7. 3 and 4 will definitely come, but after that, all we have the duplicacy in this 5, but all 5s are actually included in our MST.
So we can't take 6.
So 5, 5, 5. We can't take because we have already a smaller one before this. Yeah, if someone is raising the hand, please.
Sir,
open the
if
mic.
1 to 2 connection edge was like numbered as 5,
then there is a chance for the more MST. Because what will happen? Suppose this is a 5. Okay, now to reach this 1, we have 2 possibility: 1 2 to 1 or 4 to 1. So suppose if we are selecting this this edge first, 3 to 4, and 3 to 2 first. So there is a possibility either you can connect this or you can skip this. Okay, then still it will be connected, or you can take this and as the previous one like this, or you can also take this and you can remove this. So you will get all possibility in between these 4 vertices. So 2, 3, 4, 5. This part you have to check how many possibility are there that can be connected all the vertices.
Okay, okay, sir.
Okay, so 3 possibility are there.
So this basically is a Kruskal algorithm again.
Okay, but for the question, actually we are getting only 1 because all duplicates, the smaller one value are now included. And next, this is we have discussed this shortest path. Okay, so here this question is also similar. You have to apply the dry run of the Dijkstra algorithms, and you have to check which vertices will visited in which order. So you have to apply the Dijkstra algorithm on this graph, then you can figure out the answer. So this is the similar process which we have done. And this 4th one, we have also discussed the same question. Now this is the new one. Okay, so 5th question. Okay, so here, this is a tricky question. So here one graph is given. We don't know what is the original graph, but that graph actually contains the 4 vertices. Okay, so A, suppose we are getting A, B, C, and D, and having the 6 edge also. So that 4 vertices can be connected maximum 6 edges. So all 6 edges are weights are given, but we don't know where these edges are actually connected in the original graph. So there are lots of possibility with these 4 weights. Okay, in the original graph. So we can connect like this 3 weights on A to B, or maybe A to C, or C to D, like this. So any possibility is there. So for this connection with these 6 weights, so 3, 4, 5, 6, and 7 and 8. Okay. Now the question is the maximum possible total weights that a minimum spanning tree of G can have. So what are the possible way to connect all these 4 vertices with these weights 6H, and out of these, which actually graph have the maximum minimum spanning tree weight? So this question cannot be solved by the creating each possible graph, but here you have to apply the logic of the classical algorithms. Okay, so you can apply the classical algorithm logic. So you can pick, you can solve this.
You want the maximum, so can we go from the higher one, like
higher one?
Like
no. Here we are finding out the minimum weight spanning tree.
And in that maximum possible weight.
So suppose our graph is connected in different way. So there is a chance you will get the different minimum spanning tree for the same weights. So among these, which MST contains the maximum weight? So just telling one example. So here 6 edges are there, 4 vertices are there. So how many edges are required to create a MST for these 4 vertices? 3. Okay. Now first things, if you pick the smallest one, only one edge. So this is smallest one we are picking. It can create any cycle in the MST. We are picking only one edge.
No, in the beginning, no.
It will not create a cycle. So one edge cannot be create a cycle. Okay. So it may be connect anywhere in the graph. Okay. And we are picking this edge 3. Okay. So this edge is connected any place. We don't know this A and B, this C or D like this. This will definitely select in the MST. And it cannot be ignored in the MST. So smallest one, that means we require 3 edges. Smallest one will definitely come in the MST. It cannot be ignored, or it cannot be a part of any cycle. Okay. Now next one, 4. Can we create a cycle by 2 edges?
No.
No, sir.
No. Okay. So that means next smallest one will also be included in every MST. Okay. So it may be here, it may be here, it may be here, or it may be here like this, any place. So, but that will also included in the MST. So 3 plus 4. So this cost we have. Now we need one more edge. So 5. Now we have 3 edges. 3 edges can create a cycle. 3 edges can create a cycle. Okay. So what are the condition of 3 edges to create a cycle? So like this, suppose this is connected 3, this is connected 4. Now third edge is connected in the original graph like this, 5. Okay. First things, if we are assuming that this is not creating a cycle and this is connected like this, 5. So your MST will be like this, 3 plus 4 plus 5. Total cost 12. Okay. But suppose this is creating a cycle, 5. Then it cannot be included in the MST. Okay. Then at that time you have to skip this. Then you have to select next one. Then next one definitely will not create a cycle, because you have one possibility 5, which is already creating a cycle between this A. Now next edge cannot be create a cycle with the same graph. So definitely next edge will come in the remaining part, either this edge or this edge, not creating any cycle. Okay. So this will be picked as the next weight. So 3 plus 4 plus 6, that is 13. So these are the 2 possibility with this. So among these, this is the maximum one. If your graph is connected like this, so say A, B, C, and this next one is creating a cycle, and the remaining edge 6 is connected anywhere. And remaining these edges will definitely not be a part of the MST. So 3 plus 4 plus 6, this is the answer for this question. 13.
One question again. When you say minimum spanning tree, there are only going to be 3 edges, correct?
Yes.
So maximum weight, if we're talking about a minimum spanning tree, we'll go for the least weights that are possible. Am I wrong there? Why are we picking 6 and not 5?
So there is so original graph is not given. Na? Suppose in original graph A, B, C, D. If this is connected like this, 3, 4, and 5, and then 6, and then 7, then 8. Yes. Then can you pick? If you create the MST for this, can you pick the 5?
No, I cannot.
You cannot pick, no? So in this situation, you have to pick 6 at the place of 5. So 3 and 4 will come, but after that, you have to pick 6.
Okay.
So this is the one possible or input graph, and in that case, you will get 13 MST cost. So
No,
that is
why we cannot pick 5?
Because 5 is creating the cycle, na? So we cannot. You apply the classical algorithm here. So
5 is the edge between C, D, or how is it?
No, this is
C
and B.
C and
this one.
B. Okay, then we cannot pick. The only point I am not able to understand here is why 6. Why it cannot be 8? 3, 4, and 8. How we eliminate 7 and 8?
No, then that will not be a MST.
Because there is
here you are finding out the MST, minimum cost spanning tree. If you are picking 3, 5, and 8, then
3, 5, 3, 4 is okay. After that, I have 4 components to form a cycle.
But that is not a MST then. If you are picking if any another MST spanning tree is possible with smaller weight, and you are picking the greater one, that is not a MST.
It's not possible. Like we can create cycle with 5 as well as 6 also. Then we have
that
to
is
go
also
further.
not possible.
And then we have to go further for 7 and 8, checking for 7 and 8. We can create for 5 and 5 is for 6 cycle. Right? It can be anywhere else. It can't create cycle. Either any one of 5 or 6 can create cycle.
Yeah, 5 and 6 can create cycle, so I can go to 7, right?
No, in this situation, if 5 is creating a cycle, definitely next node will not create a cycle any place. Can you create a cycle like this? If our discrete cycle is already there, okay, so B and C, so 5, 3, and 4, and this is. Can you create a cycle with 6H any place? No. So in this situation, if 5 is creating a cycle between 3 nodes, that will not be considered. The next edge will be considered in the MST.
If 6 is creating a cycle, then we will take 5.
Okay.
No, if 6 is creating a cycle, then definitely 5 will be selected. Okay, if suppose this is 6 and this is 5 is here, so definitely this 3 will select, 4 will select, and 5 will select. Then we will not check this. So only 2 possibilities are there for this inputs, and we will find out the maximum one. So this is 13. Okay, so consider a binary tree. Okay, now the next big 6 is started. So let's discuss the big 6 question. So this is the first question regarding the max heap, but this is 3 array. Okay, 3 array binary, similar type to ternary, we can say. Okay, so 3, that means in this heap, every node will contain the 3 child at the place of 2 child in the binary. So because of that, this is 3 array, a max heap. So this definition is mentioned in the statement. Okay, so the root node is stored at location A0. Node is, okay, so this definition is completely. Suppose the elements 6, 1, 12, 8, 9 are inserted in that order into the 3 array max heap here. So this max heap is given here with this word details. This array. Okay, so we can create this max heap. So this 10 will become as the root, and after that 3 child. Okay, so label wise we will connect this. So 3, 4, sorry, so 4, and this is 5, and this is 7. Okay. Now next is 2 and 3. So this, so 2. This is the given max heap. Okay, 3-array max heap. But after that, we are inserting the elements one by one in this. Okay. Now first element we will insert 6. So 6 will insert at this place. Correct. But now this is the violating of the max heap condition. So during the insertion, we always compare the newly inserted element to the parent. If the order is not correct, then we swap. And then we repeat this process till the root node in this path. Okay, so 6, 4, 10. In this path, we will just compare this and we will just perform swapping. So 6 and 4, this is not in the correct order according to the max heap. So 6 should become at this place and 4 should become at this place. So updated one is now 10. This 6, 5, 7, and then 2, 3, and then 4. Okay, after insertion. Now next one is 1. So definitely this will insert here. So this is not violating anything. Now next one is 12. So 12 we are inserting here. So this will replace this, and okay. So 12 will also replace 10. Okay, 12 will come here. 10 will come at this place, and 5 will shifted here. Okay, in the path. Now next is 8. 8 will insert here. So 8 is smaller than 10. So now this is the 10. So no problem. Now next is 9. So 9 we are adding. So 9 will insert at the as a first child of 7. Now this is the violation. So 9 will replace, and this will be replaced, changed by 7. So insertion will perform in the same way, but this time we are maintaining 3 child. Now we are getting this max heap, and we can just traverse in the level wise. So this is 12, then 6, then 10, then 9, then 2, 3, then 4, then 1, then 5, then 8, and then 7.
Option C.
So this is the
So we
correct.
take it from left to right in that sequence.
So
Sequence
this
we take it from left to right.
yes, top to down and left to right. So this is the correct answer for this. So 1587. So 1587. I think this one. Okay. Yeah. Next is the related to the max heap again. So here max heap is given, built it by the repeatedly inserted value into the empty heap. Okay. Suppose the last value inserted was 95. What was the heap structure before this value was inserted? Okay. So first create a max heap for this. So 95, and this is now binary heap. Okay. So just create a 2 child. So 70 and 61, then 43, then 47, then 24, 47, 12, 31, and 39. Okay, this is 61. So it is saying that this 95 is inserted at the last. So that means this is the last position. Okay, last node position. So this 95 is inserted at this position, and it is shifted to the top. So if we what was the previous structure of this? If before adding this 95, what was the previous max heap?
If we remove the this 95 and then again heapify, then
no. Actually, this 95 is just added here, and now this is shifted to the top.
So sir, I am saying if we perform the delete option, delete max, then after we heapify, can we retrieve the previous heap value, heap structure?
So you are saying that you are I think you will get you will get the correct answer, but that will take more time. Okay, that will give the answer, but it will take more time, because if you know that every node insert when we inserted the node, that can be moved into the path from the last inserted position to the root only.
Yes.
Okay, so that part you need to shift only one position up.
Okay.
Okay, just shift this path to the one position upside. So this 70 will reach at this position, this will reach at this position, and this will shift here, and this will become empty. Okay, so in this manner 70 will come at the top, so 61 and 24, 47. Now this 47 will come at this place, and this will become 39, and this will remain same. Okay, this part will remain same. So 43 and 12 and 31.
So is it the same as removing the root node and then replacing the entire thing?
That is same, but it is the fastest process. Otherwise, you have to apply the EPPy process on the complete. That will take more time.
My question is, what you did is removing the root node and then replacing it, correct?
Not replacing, I'm shifting the nodes.
Shifting the nodes.
Shifting. So actually, this is 1 second. This path 95, 70, 47, 39. Because if this 95 was the last inserted node, so that means position of the insertion at this place 39.
Correct.
Okay, so just now repeat the same process. So suppose we add the 95 in this graph. So 95 will be inserted here. Okay, now it will move to the top. Okay, that means all nodes will be shifted one position down. So this 39 will shift here, this will shift here, and this will shift here, and our 95 will reach at this position. So we are performing the reverse process. We are just shifting up one node in this path, and then we are getting the answer. So after performing this, the order is 70, then 47, then 61, then 43, 39, 24, 47, and 12, and 31. And this 90, this will not come in the answer. So these are the possible. So you can see. So 70, this is comma, 70, 47, 60, 70, 47, 61. So yeah, this B, the correct set.
Yes, sir. Can we go to the previous problem for the answer? Just 12, 6, 10. Thank you.
Okay, so 1 second. 47 is 43. 40. Okay, this B is the correct answer for this. Okay. Now, next, this is also one question on the same conceptual. Min heap is given. Okay, so 10, 10, 25, 45, and 35, 38, 70, 54, and 43, and 39. Okay. Now, this time, which of the following could not have been the last element inserted into the heap? So here, last position is this. So last element can be moved on this path. So last position to the root. So that means this path can be shift. Okay. So last inserted node may come only in this element, either 10, 25, 35, or 39. If any option is not coming in this path, that will be the answer. Okay, so 25 is coming, 35 is coming, and 39 is also coming. 38 is coming this side. So this cannot be the last inserted node. Okay.
Sir, can you explain the question, please?
A question is, this min heap is given, okay, and question is saying that which of the following could not have been the last element inserted into the heap. So that means we are looking at which of the following, so out of these, which cannot be inserted at the last inserted node in this heap. Because if we are, so this is the last inserted position. We will always insert it at the level wise and the last position. Okay, so this is the last inserted position. So this 30th cannot be come at this place because this cannot be shift at this like this. Last inserted element can be shift only to this path. Last position to the root node, this path. Because at the time of insertion, we always compare with the parent. If order is not correct, then we will swap. So if you look the parent, grandparent, then parent, in this path, so you will find only one path. So we only look this path. Okay. Another something is also important. Suppose min heap is given or max heap is given. So according to the max heap, root node should be the maximum, and this is like B, C, D, E, F, G, like this. Suppose this is a max heap, so definitely maximum element will come at this position. But second maximum will always be a child of this A. Second maximum. But this is not guaranteed for the third maximum. Okay. So this is also one properties of the max heap or min heap. So if you are looking at maximum, so first maximum definitely come at the root place. Second maximum will always come as a child of the root node, any child. But we cannot say that third maximum will come at the child node. Third maybe come at the different place. So like example, we can say that. So like 10 is given, and this is 15. So suppose this we are creating min heap. Okay, so 15, and this is let me just create a max heap. So that's the same. Okay, so 10. This is like 8. This is like 5, and this is like 7. You can see 6. So here you can see we are getting this 10 as a first maximum, but this is a second maximum. But third is not. This is not a third maximum 5, but still this is a maximum heap, because third maximum may become below the second maximum. So because of that, you can see third maximum is coming at this place. So this is one condition, and another condition is in max heap, smallest element will always be come at the leaf node, as a leaf node, smallest one. Okay, at the leaf nodes, it cannot be come at the in between as a middle node. Any leaf node, smallest element can become. These are some basics about the heap you should know. So
can you please explain the previous one where you drew the 10, 8, 5, 7, 6?
So I'm saying that if you are creating the max heap, first maximum element will always come at the root place. Okay. Second maximum element will always be the child of first maximum.
Yep.
Okay. But third maximum, we cannot say that it will be the child of the root node, because it may be the child of the second maximum.
Right.
Okay, so we cannot say that this will always come, and we can also not say that second maximum. Okay.
Yes, will be the
this will always be the child of the second maximum. Okay, so yeah, this is the some things. So this is regarding this. Okay. So next is regarding the binary search tree. Yeah, now that we will look the traversing things. Okay. But first thing, this question, consider the following binary search tree. The letters indicate the names of the node, not the values that are stored. Okay. So these are the names of the nodes, but it contains some values internally that is not given, but this is a binary search tree. Okay. Now just tell me what is the predecessor node in terms of value of the M. This is the M. Predecessor means in terms of value, what is the just next smaller value?
It should be smaller than G, but at the same time is greater than greater than A.
Greater than F.
But greater than F is not there. Yeah.
Greater than A should be and less than G.
No, what's if we arrange the values in increasing order? So suppose this M is coming at this place. So what is the just previous value in terms of the value? What should be the answer for this?
Like
F.
what question, sir? What you asked? Like,
So these are the names of the node, but value is different. And we are asking that in terms of value, what is the predecessor of M? Predecessor means if we arrange all the nodes in increasing order, so what is the value which will come just before the M?
oh, it will increase in order.
Can we do the in order traversal then check?
Yeah, definitely you can do. If you apply the in order
You have to do
traversal,
the in order traversal.
if you apply the in order traversal, definitely you will get the correct answer. Okay, but you can apply directly anything. So according to the binary search condition, you know that the C value, all these value will definitely be greater than the C.
Yes.
Okay, and these value will be smaller than the C.
Smaller than C.
Okay. Now just look. So that means the C will come after this L and F in the order. And if you look the right part, so M, this M, this G is greater than. Okay, this G is greater than to M. And this G is also greater than to this G. But this C is definitely be smaller than to this G. So which value will come? Or you can directly apply the in order process on this C part, not on the complete.
On the C, yes, sir.
Okay.
Is it L? Is it L?
So
No.
before M, sir, in
It
order.
will be C only.
C, sir, it will C. Yes,
It will
sir.
be C only.
C will.
Even in order, it comes C only.
With in order, C will come.
No need to apply the in order on this part. Just figure out the what are the subtree. This is the subtree. This is also a binary search tree. You can apply the binary search that in order traversal on this part. Okay.
Yes.
So you will get the in order traversal. So that what is the process? Left traversal, then node, then right traversal. This is the in order definition.
Yes, sir.
Left traversal, then print the node, and then right traversal. So that means if we start from here, we will shift left first. Okay? Then we will shift left first. So this will become first L. Now there is no left and no right. This will be printed. Then we will move back. Now this will be printed. Okay, so F. Now we will move back, and this will be printed. Okay, so this is coming in C. After that, we will apply the right process. So this is right. Okay, now moving to this, but this L and R, this is the left first call. So moving to this, and no left right. So we will print this M, and then G, and then N. Okay, G, then N. So you can see C we are getting predecessor. If the question is asking the successor, that G will be the answer. Okay, so in order is the correct way. You can apply, but not required to apply on the overall. You can find out the subtree part and you can apply in the sort. And you can also, if you are comfortable in the in order process, you can directly figure out this.
Yes, sir.
Okay, so this is the 10th one. A binary search tree in which every node has either 0 or 2 children is referred as a strictly binary tree. Such a tree with 21 leaves has exactly 40 nodes. What is the correct answer for this?
21 leaves.
43.
Either 0 or 2 children.
43 nodes.
21. 20 will be with 2 child.
No, suppose I'm taking example, smaller example. So you can see.
So 41 will.
Here 4 leaves are there. So 3 is the another nodes. So that means if 21 are the leaves, so that means the remaining nodes will be 20.
Yes, sir.
Okay. and that will total will be 20 plus 21.
Total of 41.
One quick question here. It says either 0 or 2 children.
Yes.
So there may be some.
That is possible. So suppose if you make like this, that like this. Okay, but still you will get the same 1, 2, 3, 4, and 3. So this is the property of this type of tree.
Leaf node and internode.
Try to explain towards the end.
Sir, but it's not balanced.
We are not talking about the balance here anywhere. This is binary search tree. But the condition is given: every node contains either 0 childs or 2 childs.
If it would have asked how many will have exactly 2, then it would have created the issue. But since it is asking for either 2 or 1, then we can say, na sir?
Either 2 or 1 means?
Like in this question, if it has been asked, like how many will have only 2 childs, then multiple possibility will arise, no?
No, every node will contain either 0 child or 2 child. So 0 child means leaf node, and 2 child means internal node.
Okay, strictly. Yes, sir. Since it has been defined here strictly, that's why we are able to do this calculation.
So let's discuss this, prove this, okay?
Right?
So actually what we are directly using here, using here the leaves node. So leaves node we can write like this: n0 equal to n2 plus 1.
Plus 1, yes.
Correct? This equation actually we are using here.
Yes.
Can we prove this?
Yes, sir. I think we can go with a visualization. Like
yes, sir.
No, I'm just I'll explain by this proof. Okay, suppose we have n nodes.
20 nodes.
I'm taking n nodes. Okay, I'm taking n nodes. So n nodes, how many edges are required to connect these n nodes in the tree?
N minus 1.
Okay, this is the number of nodes, and number of edges will be
n minus 1.
N minus 1. Yes. Correct. And what are the category of each node? So now I'm not talking only for this situation. Okay, I'll also considering the one child also. Okay, one child also I'm considering here. So there are 3 category of nodes. The nodes 0 and 0, that means that nodes which have the 0 child. Okay, another category n1, that contains only 1 child. N2 contains 2 childs. So 3 categories are there of the nodes. Okay, so n0 means number of nodes which have 0 child. N1 means number of nodes which have only 1 child. N2 nodes which have only 2 childs. Okay, then we can write like this. So n equal to n0 plus n1 plus n2. This is correct?
Yes.
Okay. Now, if we talk about the in the reference of edge, so total edge we have n minus 1. Okay. Now just tell me number of nodes with 0 childs. Just look in the lower side only. Okay. So how many edge will be connected to them? 0 child.
0 child.
21. 21 edges.
No, don't look this values here. I'm just proving the equation.
Second last level में जितने nodes होंगे
one node only.
Second last node में जितने edges, second last level पे जितने nodes होंगे.
Not second last. We are looking the nodes which have 0 childs. So any edge will be connected to them.
Okay, nodes with 0 child.
Only one edge.
Upward 21.
Upward, sir, they will have, but they will no have any further.
But this is not. So you can see leaf nodes. So leaf nodes have actually 0 childs. So no edge is actually connected. Correctly. So that means we can ignore this for the edge. Actually, we are counting the edge, not the nodes here. But with the help of this number of nodes, we are counting the edge.
Okay.
Okay. So that means this number of n0 are not contributing any edge in the lower side. Now just look this n1. So n1 means if any node is connected like this. Okay, so this node is now contain only one child.
One child.
Okay, so definitely if suppose n number of nodes with one child are like 10, so definitely 10 edge will be connected to the lower one.
One edge, yes sir.
So we can say that n1 plus.
Same.
Okay, n2. Now we are looking the nodes which have two child. So that means two edge are connected below them.
Two edges, so 2 and 2.
So we can multiply this 2 into n2. Okay, now both equation we are getting here. Now we can just make equal. So this is n0 equal to, this is the first equation. Now we can make this right like this. So
n2 plus 1 is
n equal to n1 plus 2 n2. Okay, and plus 1. Now this n and n both are same. So now we can make equal. So like n1 plus 2 and 2 plus 1. Okay, now n1 is disconnected, and you can see this 2 and 2. If we just move here, and so this will remain n2 plus 1 equal to n0. So leaves node will always be one greater than the nodes which have two child.
Nodes which have two child, yes.
Okay, so this property actually works in the all types of tree, but we are just looking this n0 leaves nodes will always be one more than the two childs, that node number of nodes which have two child. So here this tree actually given with only 0 and 2 child condition. So 0 are the leaves, so that means leaves nodes are one more than the two child node. But that is also true for the another type of category graph. So like
No, sir.
Can you please explain the second equation once again? N minus 1 is equal to n1 plus 2 and 2.
This one?
Yeah.
So total number of edges are n minus 1. If we have n vertices, n minus 1 edge we have.
Right.
Correct?
Right.
So we are looking, because edges are connected to the lower side. We are only looking the lower side direction, not the upper side. So leaf nodes, there is no edge connected to the lower. Okay, that means number of leaf nodes, if we count, that no edge is connected to the lower side. So that we are not adding here.
To the
so
lower
n0,
side. Okay.
So n0 we are not meant here. But if you look the n1 means number of nodes which have one child.
One child, yeah.
So if any node is there, if one child is connected, that means one edge is connected below them.
Right.
Okay, suppose like this. So this is the node which have one child, so one edge is connected. This is the node which have one child, one edge is connected.
Right.
So we can write a number of edge is n1.
Right.
Okay, similar to the number of nodes which have one child. Now, if we look the nodes which have two child, so suppose this nodes, you can see this have two child. So that means two edge are connected below them. Okay. So here this is the one node, but it contains two edge. So this n2 is representing the number of nodes with two child. So we will multiplying by 2 to find out the number of edge.
This is where I'm having a little confusion. When we said n minus 1, we said it is the number of edges. But
actually, we are just finding out this side also. We are finding out the edges. Okay, but
two
in
edges
the
and
terms
one
of,
edge. Okay. N1 into 1 and n2 into 2, is it?
So this is representing number of nodes which have two child.
Okay.
Just convert into the number of
edges. Okay.
So we'll multiply by 2.
Okay.
This is number of nodes which have one child. So just multiply by 1, like this.
Yeah.
Okay. Now it become a total number of edge. So now these two equations we just make equal.
That was clear.
So in any graph, so not in the case.
Sir, how do you put the numbers over here? N is equal to n1 plus 2 n2 plus 1.
So let me
21 leaves are there.
1 second, just I'm clear. I'm taking one graph like here. So A, okay, B, See, I'm creating random dot D, A, F, G, or like H. Okay, so this is just a random graph. I'm considering that this is a binary search. Okay, now in this graph we have three type of nodes. So N0, I'm contributing N0. So how many nodes are leaf nodes? Actually, N0 means nodes with zero child. So you can see this F, G, and H. These are the leaves node. There's no child of these nodes. So we can say that this is a number of 3. 3 nodes we have with 0 child. Now N1. N1 nodes are number of nodes which have 1 child only. So you can see this D, okay, and B and C. All contains only 1 child. Correct? So this is 3. N2 nodes which have 2 child. So this is the 1 and this is the 1. Correct? 2. Number of 2. Now this is the value number of nodes. Now I'm saying that if our graph contains total number of vertices are here is A, B, C, 3, 4, 5, 6, 7, 8. Okay, so N equal to 8. The number of edge in this tree definitely will be N minus 1. That means 7. Okay, in this is a tree, edge will be 1 less than the N. So now we can prove, we are just proving this. Now we are calculating this number of edge, 7 equal to. In the terms, we will calculate this number of edge in the terms of this value. So leaf node, you can see leaf node, there is no edge connected to the lower side, in the lower direction. So we can write like 0 into N0 plus, okay, and number of nodes with 1 child. So these are the 3.
3.
And each node is connected with 1 edge. So we can write like this 3 into 1.
Yes.
Okay. Now number of nodes with 2 childs. These number of nodes are 2.
2.
But
multiplied by 2.
So 2 edge are connected with each node. So that means multiply by 2. So you can see 3 into 2. Sorry, 3 into 1, 3 plus 2 into 2, 4. This is now equal to 7.
Yes.
All
But
edge
sir,
we have
what is
considered.
How do we equate this 21 leaves with the number of nodes?
That question?
Yes.
So this 21, actually this is the N0 value. This value is given N0. Leaves means
N0.
and
N0.
we have proved this N0 equal to N2 plus 1. So 2 means the nodes with 2 child. So this strict vanity is given. So we have only 2 types of nodes which have either leaves or the mediator node. Okay, so 1 child node is not there. So we can directly use this condition. So N0 equal to N2 plus 1. So N0 value is given 21. So 21, just reduce this minus 1, it becomes N2. 20. So now 20 plus 21. Just add both, you will get 41. Okay. Number of nodes with the 0 child and number of node with the 2 child. Add both, you will get the total number of nodes. Okay. And this property is also okay with the 1 child node graph. Okay. So here you can also see how many. Here this property is also true. N2 plus 1. So N0 you can see 3. Okay. And if you find out the N2 value, so this is 2. Okay. So 2 plus 1. Correct. Okay. So in this tree, 1 child node is also there, but still this property is true. We have to prove this. Okay.
So if 1 child nodes are also there, then you will need at least 2 of these, no? Either n or n2 or n1. These values should be given, no?
So I just
In a question, I'm talking hypothetically. If one child nodes are also present, then some other information will also have to be given in
yeah,
the
that type of question may also be
question.
asked. Suppose this information n1 is given, okay, and n value is also given, total number of nodes.
Then it is easier to calculate.
Then you can also calculate the n2 or n0 things. Okay, based n number of edge are given, so you can use these formulas because now you know that n0 equal to n plus n2 plus
N
1.
is equal to n0 plus n1 plus
That we have also checked, the n equal to n0 plus n1 plus n2. Then you can also use this formula. Okay. So if some information is given in this manner, you can apply this equation and you can figure out the answer. Okay. So this is the one question. Next one is, okay, the maximum and minimum number of nodes in a binary search tree of height 7. Consider that the height of the empty tree is 0. So that means empty tree height is 0. If we are considering one node, then height become 1. Okay, and if we add, make this as a complete full binary tree, this full binary tree, so now height is 2 for this. So you can see for height is 2 equal to maximum node is 3. So in this manner, you can figure out that what is the minimum and what is the maximum possible nodes with this height 7. So
Sorry,
if single node,
when you say height is 2, or is it height 1 in this current scenario?
no, the base case
0,
is
1,
given.
Base is always counted as, okay.
No, not always. It will be given in the question if this type of question will be asked. So in some books, the that height of the single node will be considered as a 0, but in another books maybe height will with the single node will be considered as a 1. So that will be given in the question.
So we should go from 0, 1, 2, 3, 4, 5, 6, 7, or what exactly is the definition of height there?
The height definition is given if there is no node in the binary search tree, that height is 0.
Right.
If we are considering one node, then height will become 1.
Height is 1.
Okay. If we are adding one node, then height will become 2.
Okay.
So height is starting from the 1 in the non-empty binary search tree.
Yeah.
Okay. So now in this case, what are the minimum and what are the maximum nodes possible with this height?
Sir, I have a question. Can I ask? Sir, when in question it mention balanced tree, then we consider it balanced, else we don't.
If it is not mentioned that the binary search tree is balanced, then do not consider as a balance.
Sir, D option.
So that we will check. So here it is starting from the 1 in the non-empty binary search tree. So definitely, if all nodes are connected in this manner, that will be the case. 1, 2, 3, 4, 5, 6, and 7. Okay, that will be the case with the minimum number of nodes with this height. Okay, so the 7, yeah, definitely minimum will be the 7. So either B or D. For the maximum, you have to apply the formula. So you can just create a formula for this. So, for the smaller examples. So here, if you have only single node, you can write like this. So height is 1. Okay, height is 1 for this. So 2 to the power h minus 1. Sorry, 2 to the power
h and outside minus 1, like overall minus 1.
2 to the power h over minus 1. Yes, correct. Okay, so this formula you can make based on the base condition, and if you take the height 2, so 2 to the power 2 minus 1, so 2 to the power 2, 4 minus 1 equal to 3. So you can see 3 is the total number of maximum possible. Now you can apply this formula to the 7 nodes. So 2 to the power 7 minus 1.
128.
So this 128 minus 1, 127. So this one is the If suppose this is given like single node height is 0, okay, if in question it is mentioned that the single node height is considered as a 0, so in that case you have to change this formula. You have to write like this: 2 to the power h plus 1 minus 1.
And that
Okay.
minimum case would be also h plus 1.
So in the based on the base case, you can create your formula by just looking the smaller example. So this is the answer for this. Yeah, this is the last question in this, and let's just look the mock. Okay, yeah, the mock question, this is mentioned 6 questions. Consider A. Let me just zoom it. Consider a binary tree with 20 nodes. Okay, here n value is given. Okay, so this is the question which we can solve that by that. Consider a binary tree with total 20 nodes. So this n value is given. Okay, 20 nodes. Then number of edge will be 19. Okay. Now where the number of nodes with 2 child, so that means n2 is given 7. The number of nodes with 1 child, so n1 is asking.
So
5.
n0 will be 8.
Yes, sir.
And
8 plus 7, 15
minus
minus 20.
So what is the answer?
5.
How will you compute n0, please? Once again.
N0 is actually it is mentioned. Okay, n2 value is given.
Yes, sir. So we can get
so
n0.
N0 you can get 7 plus 1, 8.
And n1 plus n2 plus n3 will be n.
So this is n equal to n0 plus n1
plus
plus
n2.
n2.
Yes.
Okay.
So 8 and 7.
7 plus 8. Like this.
We can eliminate that part, like edge se jana wapas se.
8 plus 7, 15, and 15 and 5. I will be the answer.
So the relationship between n2 and n1 is the one that you actually showed earlier.
Yes.
Okay, n2 is equal to n1 plus.
Yeah, that relationship we applied here to find out the n0 value. After that, we know number of nodes will be n0 plus n1 plus n2.
N2, yes.
This equation.
Okay.
We can apply we can put the answer. Okay.
Yeah.
So next.
So here n0 is how much?
N0 is 5.
8. Okay.
No, N0 is 8.
N0 is 8.
So that we calculated using this N0 equal to N2 plus 1. Okay. N2 value is given 7. 7 plus 1 equal to 5. 8. After we got 2 value N2 and N0, and this is we are asking. So N is also given. So this equation we also have. So you can put this and we can get this N1 value. Okay. And okay. So your 7th question, this BFS is performed on a binary tree beginning from the root vertex. Let the distance of the node represent the number of edge from the root, okay, to that node. If a node V is at distance 4 from the root node, and this is the last visited vertex in this BFS traversal, then the maximum possible number of nodes in the binary tree is. Okay, now can you link this BFS to the binary tree traversal and just figure out the answer? So any binary search tree is given and like this, and we are applying BFS on this root node. So BFS will traversal like definitely adjacent wise. So this node will be traversed first, then this will be traversed next.
Okay. Level wise, no?
Level adjacent wise we can say. Yeah.
Okay.
In tree we can say also level wise. So, and distance definition is given number of edge in the path. Okay, suppose this is the node and this is the root. So what is the distance in between? 2. Number of edges is 2. So now the question is this: the distance of node is given 4. So what are the maximum possible number of nodes in the binary tree?
And sir, 4 edges, matlab 4 height.
4 height for this. So this is like
Maximum nodes will be 31 then.
so till here. So this is the last visited node. Distance is given. So till now 3 distance is there, and if we traverse one more level and like this, so minimum and maximum possible. So minimum distance will be if suppose we have only one node and this part is not there. So this may be also the question. So what are the possible? So this is the last visited node with 4 distance. What are the minimum number of node possible? So in this case,
It's to 4 plus 1.
2 to the power 3 minus 1.
2 to the power.
Not 3, 4. So 4 minus 1.
4.
Sir, here height is
Plus one.
considered as like empty.
Height is 4 plus 1, no?
Actually, this definition is given now.
2
So
raised to
a
4
node,
plus 1 minus 1.
If a node B is at a distance.
this is given distance. Okay, the distance of a node represents the number of edge from the root to that node. So this is now you can apply any. If you are applying 0, that still you will get the distance. This is not here. Height is not given here. Distance is given. Okay. So distance you can see for the minimum case. So now till this level we are getting 3 distance. For minimum case, if suppose we visit only one node. So suppose this is the last visited node. So in this case you have 15 and plus 1 16 nodes. Okay, but what is the maximum one? If
31.
all are completed. Okay, and it will become a 31.
Sir, can you please explain the minimum case again?
So suppose it is mentioned that if last visited node height, the distance is 4, then the minimum possible number of nodes in the binary tree. Okay, so this is possible if only one node is visited on the last level. Okay, now the distance of this node is 4. So this is the minimum case.
The minus 1 will not be there, no, for minimum case. 2 to the power n will be for minimum case.
Minimum case, the last node will be only on the last one.
For minimum case, 2 to the power d, sir.
Only one leaf on the last one.
So when I have a one fundamental question. When you say distance, are we referring to the number of edges
in the path from root to that node?
Okay.
So you can not apply this direct formula. Yeah, you can apply, but this may work only for the one situation. But here you can simply figure out this 3 distance. Yeah, 4 distance is possible for all these nodes on the last level, correct? Okay. If only one node is traversal on this level, that will be the minimum case. If all nodes are,
and if all are there, then it will be the maximum.
This is the maximum one. Okay, for minimum it will become 16, and for maximum it will become 17. After that, if we traverse one more node, then height will increase. Sorry, distance will be increased for that.
Then how the 16 come?
No, it should be summation, isn't it?
Till here. So this is the height of 4. Okay, if we consider the root node at height 1, so this is the height of 4. I'm talking about the height of 4. So 2 to the power 4 minus 1. So to 16.
Okay, for this you are talking.
No, but they say BFS, right? In BFS, levels are 1, 2, 3, 4.
So that BFS will be
root, right?
Yeah, BFS will traverse adjacent wise.
No, that's clear. But as per the definition, they don't consider the root as level 1. Yeah.
No, it doesn't matter. It consider 1 or 2.
But the answer will differ, right? Yeah, answer will differ, right?
Why?
Because if I leave the root node, then 4 will be 2 power.
No, we are not looking these things.
5
Here we are
minus
considering
1,
that
right?
this, we are considering this distance. This distance is definition is the main here. Okay, so here distance is mentioned. So distance is coming from root to level, root to leaf node. How many edge are there? We are
Yes.
counting the edge. So according to the definition, for 4 distance, that
Yes.
means 4 edge should be there in the path.
So it is 2 power 5 minus 1, right?
Huh.
No, 2 power 4.
That is maximum.
Yeah,
For the
maximum.
maximum case,
Maximum 2 power
if
5
all are
minus
failed,
1.
Yes.
And the minimum will be 2 to the power 4.
No, why it should
2
be
to the
2
power
power
4 minus
4?
1 plus 1.
No, why
Because,
it cannot
2
be
to the
skewed?
power,
Why it cannot be skewed?
it is a binary tree, no?
It is
Binary tree is it can be skewed.
Actually, we are using BFS. That's why it can't be skewed, I guess.
But here we are looking
you can
for
use
the
BFS in any no. Okay, maximum is clear. It
Okay,
is 2 power 5 minus 1. But minimum, why it cannot be skewed, and it can be it is 1, 2, 3, 4, 5. It can be 5 nodes only minimum.
yeah, correct.
Yes, for minimum it will be.
Yeah. So you pointed out the correct things.
If
Yeah,
it has been mentioned the
if
BST.
this is given as a binary tree, definitely you are correct. So we can directly going like this.
तो BST
But
होता तब
suppose
जाते हैं इसके साथ.
no, BST is also not correct. If suppose it is given that this is a complete binary tree. Okay.
If it is a complete binary tree, then
Okay.
it will be 2
Okay.
to the power 4.
It will be
And to the power n.
Not BST,
BFS
complete.
is binary tree.
Yes, sir, complete binary.
Yeah, if only mention that binary tree or binary search tree, so that means this is also a minimum case.
Yes, sir.
With the same height.
But we're looking for the maximum, isn't it?
But if we are looking the maximum, that means all should be filled.
Then
all should be filled.
Full tree.
And then it cannot be 2 power 4 minus 1. It should be 2 power 5 minus 1, correct?
That we can
2
simply
power 5, 4 plus 1, no? 2 power 4 plus 1
No, 2
minus
power
1.
4. If you say 2 power 4,
Height is 4, no?
Yeah, so if we are considering the number of edge in the path,
2 to the power
we
4
have
plus 1 minus 1. 2 to
no,
the
if we
power
are
height plus 1 minus 1.
If we are considering the edge in the path, so definitely we have to increase one height. Okay, so for height, if we are considering the number of nodes in the path, then so we have to change the formula accordingly. So you can simply change the things according to the given information. So we cannot directly put the formula based on
correct.
the.
That's exactly what I'm trying to ask. Actually, is it 2 power 4 minus? Because if
No,
you
it
say
is not.
first layer is 2 power 0, second layer is 2 power 1, third layer is 2 power 2, 2 power 3, and 2 power 4, then it is a sum of all these, which is actually the number of
Sum of
nodes.
you can say sum of nodes. Yeah, 2 to the power 0, 2 to the power 1, 2 to the power 2. Yeah, this is the sum. Actually, this is the different things. Here we are calculating the number of nodes on each level.
Correct, but that will be the maximum number of nodes on the binary tree, correct?
But each level. So suppose till here 2 to the power 3, and so if you add all these, so you will get this equation. So 1 plus 2 plus 4 plus 8, you will get 15.
So that will be
But
15.
that will be
plus,
distance of 3. It is not distance of 4.
no, when you are taking the minimum
this
distance
of this
of
is
4, you have to add one more, no?
Can you just hold
So
on,
that
please?
is when it will
Can you
become
just hold on, please?
15
Rohan,
to
just hold
16.
on. Just hold on. Distance, is it edge or is the vertices?
Edge.
If it is
According
edge,
to
then
the
we have only
question,
3 vertices over here. Sorry,
Yes,
we have only 3 edges over
fourth,
here. If we have the
fifth.
4th edge, then it is 2 power 4 also should be added.
For maximum
Yes.
case, you have to add this also. So then it becomes 31. So this level we have to add for 4. Actually, I'm just talking about this minimum case. If this is a complete binary tree.
That is clear.
Yeah.
Absolutely, that is clear.
So don't use any fixed formula, okay, which you have learned any before in any place. So just figure out that what information is given and just change the formula according to the given information. Okay, so base case may be different. Here distance is given in the form of number of edge. Suppose this distance is given in the number of vertices in the path, then it will become different. So this will become a 5. So in that case, suppose the distance definition is given number of nodes in the path. So your tree will complete on this level. Okay, on the above one. So 15 will be the answer on this case. So change the formula accordingly. Suppose if the distance definition is given the number of nodes in the path from root to leaf, so that 4 distance will be represented by only 4 levels of the tree. Okay, here distance is given as the number of edge in the path, so that means we have to increase one more level.
H plus 1.
Okay.
Okay, sir.
Okay. Okay, just check the next. Yeah. Priority, this is mentioned 2 new element. Okay, so I think this is you can do.
Yes.
Max heap is given, just insert 10, then convert into the max heap. After then insert 17, then convert into the max heap. So this insertion will be not at the one time. After every insertion, you have to convert into the max heap.
Yes.
Okay.
If it is okay, can you just solve this one?
Okay. So here this max heap is given, so 20, 18, and 15, 13, 12. Okay. So we are inserting 10. So 10 will be inserted here. Okay. So this is a max heap. So no. So this 15 is already greater than. Okay. So nothing is happening. Now this is still max heap. Now 17 we will insert at this place. Now 17 and 15 we will compare. So 17 is greater than 15. So this will be swapped. 17 will come here and 15 will come here. Only one operation is required. So after 17 and 20 are in the correct order. So now 20, 18, 17, 13, 12, 10, 17. Sorry, 15.
Okay. Right.
Okay.
Thank you.
So this is the, and this we have already done. This AVL tree. So AVL tree we will consider in the big 7. Okay. So now one question someone is asked in the initial of the session. So that ordering thing. Okay. So let's discuss this. Suppose one binary search tree is given. I am creating one binary search tree because we have to create the order, all order. Okay. First. So I am creating one small binary tree. So like 15 and 10 and 20. This is 5 and this is 5 3 1 6. Okay, 1 second, 5 and this is 12. 18, 25. And one possible case where the period and post order actually will fail, that will I will take this order. Okay. Okay, so first we'll discuss these things, so how we will get the order, but I'll also check the pre-order and that post-order thing. So what is the in order for this? In order, pre-order, post-order. Can anyone tell me pre-order for this? So pre-order according to the in order definition. First in order, okay. So left traversal, then print the node, and right traversals. Okay, so just use this formula. So we will apply from the root nodes. So left traversal, we will move to this side. Okay, and then again this side. So 5 will come at the first place. So everyone know the ordering things. Let I discuss the completely.
It would help me
if
you say it. I don't know about the rest of the colleagues, but it'll really help me. Thank you, because I've been breaking my head about this since yesterday.
Actually, we are just applying the recursive approach for this. So this L and R, okay. So this is for the n order traversal, where this is a actually L. L means left recursive call. That means we will apply all 3 steps to the left child. Okay. Right is a right that the same algorithm we will apply on the right child. But this n means we will traverse this node and print. Okay. So we in our algorithms we have only 3 steps for each node: left traversal, print node, and right traversal. So this is the order of these 3 steps. Okay. And we are applying this 3 traversal on the root node. So these are the 3 steps, and we will perform left to right. So now when we are just performing this left, so this is a recursive call on the left child if it is available. So that means we are jumping to the next recursive call, and all same steps we are performing on the left child. Okay. Once again, the first step will be executed in the recursive call. Now this is same recursive call to the left. So now we will jump to the left child, and same step we will perform here. Okay. Now there is no left here for this. So this step will remain empty. So this is now base case here. Okay. And we will not continuously recursively call. So now second step is print statement. So that means 5 value will be printed first. Then right step, right recursive call is also not there. Okay, right child is not there. So this step will be completed. Now all 3 steps are completed. We will return back to the call. Okay, recursive call. So now this L part is completed. Now n, this print statement will perform. This will print the current node. So this 10 will be printed here. Okay. Now right recursive call. So right recursive call, jump to the right child if it is available. Okay. So L, N, R. Now left, first step, no left. Then second step, print, 12 will print. Okay. No right. Now this part is completed of the call. Now this is all 3 are completed of this. Reverse back. So this left is completed. Now print statement. Okay. So this 15 will be come. Now right recursive call. Okay. So L, N, R. So left recursive call. Just move back this side. So this L, N, R. And L is not there. Print statement 18 will print. And then no right. Move back. And that second step 20 will print. And then right recursive call L and R. So this will print it 25. This end. Now all are complete. So this right part is completed. Now this part is all steps are completed. Okay. So you will get this order. So this is a in order traversal. Now we will apply the pre-order. Okay. So I am creating a new tree. Same. 20, 5, 12, 15, 25. So for pre-order we have the formula. Pre-order means print statement should be performed first. Okay. So that means N, L, R. This is the only change. That print steps will come first, then left recursive call, then right recursive call. So this we will apply recursively. So N, L, R. So N is the print statement. So 15 will print first. Then left recursive call. Okay. So jump to the left child. Okay. N, L, R. So now this is the first step. 10 will be printed. Now L and L, R. Okay. Now print statement 5 will be printed. And now left is not there, right is not there. Reverse back. L is completed. Now right recursive call and L, R. Okay. N 12 will be printed. Now no left, no right. Left is completed, right. Okay. N, L, R. Now print statement 20. Then N, L, R. So print 18. Okay. Now left, right is completed. No left and L, R. 25. So this is the pre-order. In pre-order, we will always get the root node at the first place. So this is the pre-order. Now similarly, post-order. 15, 10, 20, 5, 12, 18, 25. Okay. So now the in post-order, this N will be performed at the last. So L, R, N. So L R. So left recursive call L R N. First step left L R N. Now no left, no right N. Okay, so 5 will be print first. 5 will be print. Now all are completed. Second step is right recursive call. So move to the right L R N. And no left, no right N. So 12 will be print. And this part is completed. Now this N will be performed. Okay, so 10 will be print. Okay, now this L part is completed. Now move to the R. So L R N. Now move to the left. So L R N. No L, no R. 18 will be print. Okay, and so now this L is completed. Move to the R. So L R N. So left, no right. 25 will be print. And then this part is done. So right is done. And 20 will be print. Now this part is completed. So now this N will be performed. 15 will be print. Okay. So this is the post order. So post order, we will always get the root node at the last place. So in this situation, this is the this ordering we are getting for the binary search tree. So if suppose you are giving binary search tree order, either pre-order and post order, you can create a binary search tree by this. So how you can create? Suppose pre-order is given. I am talking about the binary search tree, not the binary tree. So if binary search tree is given, you can reconstruct the binary tree only from the one order, either pre-order and post order, but not from the in order. Okay, because in pre-order, you know what is the root node. Root node coming at the first place. So 15. So you can simply reconstruct the binary tree. So just traverse node one by one from left to right in pre-order and simply insert each value by the same logic of the binary search insertion. Okay, so 15 is the root node. 10 will be come onto the left. Okay, so 10. 5 is smaller than 15, smaller than 10, then it will come here. 12 is smaller than 15 but greater than 10, so 12 will come here. 20 is greater than 15, so come to the right. 20. And 18 is greater than 15 but smaller than 20, so it will come here. 25 is greater than 15, greater than 20, 25. Okay, you can see we can simply construct. So we are getting the same input graph. But in insertion, just always remember this: when we are inserting the new node, always start comparison from the root node and just start comparison from root node to according to the value. When you find the empty place, insert at that point. Okay, do not directly insert. Suppose you are getting 25, so do not directly put at the by looking the lower values. Always start comparison from the root node. Okay, and similarly, if post order is given, start from the right to left. This is the root node. Okay, so 15 and take 20. So 20 is the greater one, so will be add on this place. Then 25 will add here. Then 18, so 18 is greater than 15, smaller than 20, so 18 will add here. Then 10 will add here. Then 12 will add here, and 5. Okay, now you are getting this same. But if in order is given, then you cannot find out what is the root node. If in order is given, you cannot figure out what is the root node. So because of that, we cannot reconstruct the binary search tree only from the in order traverse.
Even if somebody, even if a hint is given that it is a full tree.
Huh.
Sir,
no, that is not the case. But actually, in order traversal, you are not sure that which position the root node. Okay, you are saying that it is if it is a full tree,
yeah,
then it will come in between. But still,
yeah, it will always be in the center, isn't it? 2 power n minus 1 is where it will be.
Yes, but then how you will traverse the node?
Yeah, that's the bit I'm still not clear about.
With only in order we cannot do, I think.
No, Wait a minute. Why would that not be possible? Okay, in this one, maybe if it is longer, I don't know.
In order, the
Suppose you
elements are
figure out this is
in
a root node.
ascending order.
Then
And
how you will?
we don't know the.
You don't know which node should be insert at this time. So
Exactly.
suppose if you traverse this side, then you will get wrong. Okay, so this 12 will directly connect to the 15 left child.
How many to leave and how many, which one I should consider will not be clear if the sequence is long. In this, it is okay, it's evident, but yeah.
Okay, so this is the case for binary search tree. But if suppose the same things we are creating for the normal binary tree. Okay, so just assume that this is not a binary search tree. So there is no logic for this insertion smaller than and greater than.
No, for the in order, if it is balanced, then we will be able to find it.
But why? How?
So, balanced, I will be having all the elements, right?
All the elements, but how you will figure out the first thing, root node? So yeah, you can
root
figure
node
out
will
the
be
root node
the
will be
middle,
element.
and every root node will be in the middle, and then one to the right and one to the left will be odd. Again, we will be having the middle element, right?
You can apply some strategy. Suppose if it is full, then you can figure out this is
That is
root
what I
node.
say. Balanced means full, complete
15.
balance.
Okay, yeah. After that, in this part, this will definitely come on the left. This will definitely come on the right.
I'll be having the
Then
middle element
you will
always.
pick middle element again. So like this 20. So in this way you can connect, but this is only the case when this is the full. Then you have to apply this.
Full. Just for the case only. In order full, then only we can find the.
Yes, you can find.
Tree. And in the question always they were telling, two orders are required to construct. Why is it so? Because with pre-order we will be able to. Pre-order we are able to do, and then post-order also we are able.
That's only for the binary tree, not binary search tree.
Not binary search tree.
It's only for the binary tree.
Suppose now if we talk about the binary tree, okay.
In that, sir, in order can be different, right?
Order can be different. I'm just creating another ABC, like A, B, C, D, F, G. Okay. Now there is no relation in between the values. Okay. Now just traverse in order. So first we have to find out the in order, pre-order, post order. Okay. This time I'm not running full algorithms. I'm writing quickly. Okay. So D and
D,
then B, then E, then A, then F, then C, then G. Okay, in order traversal. Then pre-order traversal will be pre is N L R. Okay, so A, then B, then D, then E, then C, then F, then G. Okay, and post order is L R N. So D, E,
D,
B, and then F,
G,
F, G, C, A. Yeah, correct. Okay. Now this order is given here, and now you cannot figure out that which value is smaller and which value is greater. Now this is simply binary tree. In this case, you have at least two pair. So either in order and pre-order. Okay, and in order or post order, or pre-order and post order is also possible. But in some case, it may our reconstruction tree may be different. So first thing we will discuss in order and pre-order. Okay, suppose these two values are given. So let in order and pre-order. So D, B, E, A, F, C, G, and pre-order is A, B, D, E, C, F, G. Okay, so how we can create? In pre-order, we can see first node is a root node. This is a root unification. So that means we can create a root node, and we will just traverse the node from pre-order from left to right, but we will check in the in order. Okay, so this A is coming in the in order on this side. Now all the nodes which are coming on the left, that definitely will become the left side of this, D, B, E. Okay. All these nodes which are coming on the right side, so that will become on the F, C, G to the right in the tree. Now just pick the second node, B, from this side. Okay, so B. So that means this will become a child of A. Now the nodes which are coming to the left will come this side, and this will come this side. Okay, and now this is a single node, so this is coming D node, and this is E nodes. Now the same things, C. So C will become the child of A, and the F will be the left child, and G will be the right child. Okay, F and G. So we can reconstruct this. Okay. Similarly, post order, in order and post order. So in order, post order is like in order D, B, E, A, F, C, G, and post order is D, E, B, F, G, C, A. Okay. Now post order, you know, last element is the root node. Create the root node and traverse the nodes from right to left, this post order, and check in the in order. So you can see A is the here, and all the nodes which are coming on this side will become on the left, D, B, E, and this will come on this side, F, C, G. Now next node is C. Okay, so C will become a node at this level. Now F will come at the left, G will come at the right. Next is B node, F. Okay, now B. So B will become a node, D will shift it this side, E will become a node, and D will become a node. Okay, now you got the tree. Now pre-order and post order is given. Okay, so that is the case. So let's write this. So A, pre and post. A, B, D,
E, C, F, G.
E, C, F, G. Okay. A, F, G. And post order is this D, E, B,
F, G, C, A.
F, G, C, A. Correct? So in this situation, we know that what is the node of this root.
Root is A.
Root node, we know that. After that, we don't know what is the left node and what is the right node. Suppose we are just assume that this is a C, this is C1 and this is C2. Now we will check what is the value for the C1 and what is the value for C2 possible. Now we will check this. So this is now become a root node, and for this, so you can see the value in the pre-order, okay, and value in the post order. We will look both.
Yes, sir.
Okay, so post order and pre-order. So what value is coming to the
left?
This yeah. So the value which are coming to the right in the pre-order, that will become a C1. Okay. This node. So this will become a C1, and the value in the post order which are coming just to the left, that will become a C2. Okay. If both are different, there is no problem. Actually, this is C. Yeah. If both are different, there is no problem. We will directly connect. Okay. In some situation, we will get both same. At that time, actually, our graph will become a different. So we will check this case. If we are not, for this example, we will not get. But suppose if any node have only one child, so in that case, you will get the same value. So in this case, we are getting this correctly. Okay, so B. So this value C1 is B. Now this is replaced by B, and this is replaced by C. Okay. Now we have marked this. Okay. We will also mark this. Okay. After that, we are looking for B child. Okay. B child. So C1 and C2 for B. So just check the B. What is coming after that? B, D, So
Yes,
that will
sir.
become a left child C1,
Left
okay,
child.
for B. And what is coming? This is the B, na? So what is coming to this side?
E.
E. So that will become
C2.
C2. So both are different. Just connect correctly. Okay. So D and this is E. Okay. And also mark in the both. So C is also included. That B is also included, and now D and E is also included. Okay. So D and E, and D and E also included in our tree. Now just we are looking the child of C. Okay. So for C, C1 and C2. So for C1, what is the value which are coming to the right? F. Okay. And in this C, what is the value coming? Okay, G. Both are different.
Yes, sir.
Okay, so that means F will connect here and G will connect here. Okay. Now all are marked. So we are getting correct. But in some case, if any node have only one child, that will be the problematic. So
that's only in the case pre and post are used, correct?
In the pre and post case for the binary tree.
Like
Rest of the combinations we can do it.
How will it create issue, sir? Will if it will have
So,
one?
let me just have to create one example for this. So let me just figure out that. A, B, E. Okay, yeah, this is the binary tree, na? Okay, okay. So suppose we have this graph. So A, B, and C, and this. Suppose this is only D. This is E. This is F. Okay, like this. Okay. Now, what is the in order for this? Or just calculate the pre-order and post order. Okay. So what is the pre and post?
A, B, D, C, E, F.
A, B, D,
C, E, F.
C, E, F. Yeah, correct. And post order?
D, sorry, D, D, E, F, C, A.
Okay. Okay, so these are the given now. Okay, same things we will apply here. So A we know. Okay. Now what is the C1 and C2? Okay.
B and
so this is B and this is C.
Right, C.
Okay. So this is become B and this is become C. Now in this case, we have marked B and C and A and B here. Now we are looking for the B. Okay, so B and C1 and C2. So for B, C1, you can see we are getting D
as the left child.
So D, and for this side again we are getting D. So you can see both we are getting D. Now we cannot figure out that this C, where we should put this D,
in the left or right.
Left or right. Okay. So suppose if you connect onto the right, and remaining will be connect correctly. So EFF. But still you will get the same pre and post order for this graph also.
Child.
Yes, so the same pre-order post-order for both graph you will get, and but the original one was this, but you are getting this.
Exactly.
So this is the condition. If you are getting both child same, so you can put on any sides, either left or right. It will not affect your pre-order and post-order.
But it will affect the tree, right?
It will affect the tree.
So for that we should have in order.
So
that's why we should have a complete like full tree we should have.
That is the requirement, but still if we are getting this tree, it will also produce the same pre-order and post-order. So because of that, we also say that it is not returning the incorrect information, but it is creating another possible.
We got the different tree.
Possibilities are there. But it is also working. Pre-order and post-order, we also can create. But this is the case when we will get the different. Okay.
I have some basic doubt. This binary tree and then search tree, what is the
Binary tree is just binary tree is just a nodes with 2 childs, maximum 2 childs. Okay, binary search tree is a with the condition. The binary search tree is also a binary tree, but that contains the condition with every left node will be the smaller than the parent.
Only that is the only difference.
Yes, right child will be the greater than the parent.
Okay, the next is when do we use binary tree and then search tree? What is the significance of having? Do we have any real utility application?
Application we have binary
tree. Search tree at least we have something, but binary tree, do we have anything?
Yeah, so that if you remember that prefix and postfix, that infix expression, prefix expression, I think we have already discussed this in the stack week 3, I think.
Okay.
So this there is one example for to generate the prefix or the postfix expression. So how actually computer solve the expression? Suppose this expression is given like this: a plus b, my into c.
Expression tree.
So this expression is given. So that is actually not directly solved in this manner. First, it is created either in prefix or postfix expression. So that you can create using the tree for this expression. Okay.
That we used to solve in stacks.
Yes, correct. So suppose you can create a tree for this expression. So that tree will be created like this. So pillars, this a and this is the into, and this b and this c. Okay. So operator will come as an internal node, and this value will become at the leaf node. But after that, you can apply the pre-order traversal for this. You will prefix expression for this. Okay. If you apply the post of this on this, you will get postfix expression. And that postfix expression can be solved by the stack.
That is more convenient than stack, using the stack.
Yes. Using the stack, you can easily solve the expression, postfix expression. So that is actually one example of that binary tree. Otherwise, your directory is also connected in this binary tree form.
Hierarchy.
Not binary tree, but tree forms, we can say.
Tree forms.
Tree forms.
Hierarchy.
Okay. And this pre-post in order is all for the operations, is it?
Yeah, these are the traversal. Just a traversal. Okay, we can traverse the tree in 3 different manner: in order, pre-order, and post-order.
Do you have this expression in the syllabus?
No, that is not in the syllabus. That yeah, that is the application of a stack, but we can generate the prefix postfix expression using the tree.
Using a tree, yes.
Thank you.
Other Hoopman codes, we are also using this tree application where we are generating the Hoopman codes. Okay, so that is also one application of tree.
Like so in the Hoopman code, there was a statement like in Hoopman algorithm that always generates prefix code. What does
prefix code means? That actually definition is always generate the prefix code. And what is the prefix code? If we are getting A, B, C, D. So if we are getting like code for A01, okay, so that means this 01 complete code should not be come as a prefix in the another code. So our code of B cannot be look like this 011.
No, it will not look like.
Okay. So if our code contains this property, that codes are called as a prefix codes.
ओके क्योंकि हमारे पास डिलीमीटर अलग से नहीं है, तो जो पहले आने हैं उनको पहले आ जाएंगे.
Actually we are simply traversing from root to leaf, and we have unique path for each node. Okay, so that is not possible. Okay. So that is called as a prefix code.
Okay.
So I think this is okay, all covered. So week 5 and week 6 covered. So just questions will be on the same lines, okay, which we have discussed. So now practice on this. Now, next session we will discuss week 7 and week 8 questions.
May I impose one last request on you? Prim's algorithm,
Hmm.
can you actually show one, please? Because I'm very comfortable with Cruscal.
Okay, Prim's algorithm.
Prim's, yeah.
Okay, I'm applying on the one graph. Okay.
Yeah.
Suppose I'm taking this graph. Oh, okay, what is it? So I'm applying the dry run of the Prim's algorithm and how it works. So suppose this is an input graph. We can apply the Prim's algorithm from any vertex. Okay. So similar to the Dijkstra algorithm, one source vertex is given, but Prim's algorithm we can apply from any vertex. And suppose we are applying from this vertex 1. Okay, so we will also consider the same things. This will be the 0 and this all will be the infinite. After that, we will just look. So this is the first visited vertex. Okay, so I'm also marking the visited order for this. So this first visited vertex. After that, we will update the distance from which are connected through this one directly. Okay. So if we are getting a smaller one, then we will update the previous one. So here you can see 1 to 2, we have 6. Previous is
infinity. We'll change it to 6.
Okay. Now this will be updated by 5, correct? And this 3 will be updated by 12. Okay. Yeah. Now we got this. After that, we will look all the smaller one. Which one have the smaller one, and which is not visited yet. Okay. So which one is the smaller?
I will start with 4.
No.
Oh, okay.
The distance on the vertex.
Distance.
Okay, correct. Yeah, this 4, yeah, this one. Okay, so this is now visited. Now this will be the second visited.
Yeah,
correct. 4. Okay. Now from this, so that means if you are coming on this 4, so that means this edge is now selected.
Yeah.
Because this weight we got from this one.
Correct.
Now this weight will be selected. Now we will check. We will update the distance from this 4. Now this time we will not add the distance of the previous one. So
no
from 5, okay, 4. So 4 to 5, 4 to 3 is connected with 5. So we will consider only 5. We will not add the previous distance.
Okay.
This time. So this 4 to 5 is 5 and previous is 12. So this will be updated by 5.
5.
Okay, so we will also mark that this we are getting from 4.
And 6 is 10.
And this 4 to 6 is now become 10.
10. Okay.
Now this is the updated one. So this is visited, this is visited. Only 2 are connected. Okay. Yeah. So now just check again. Which one is the smaller?
3 is smaller.
3 is smaller, so 3 will be select first. Next. Okay. So where from we are getting this 3? This.
Yeah.
Correct. So this edge will be selected. And now we have selected 3. Just update the distance from 3 to non-unvisited. Okay. So 2, 5, and 6 are remaining to visited.
Yeah.
So this is now visited. And you can see 3 to 6. 3 to 5 is 6. So it will be updated. And this is we are getting from 3. Okay.
Yeah.
And 3 to 6 is 4.
Okay, 3 to 6 is 4. Okay.
So this will also be updated 4, and we are getting this is from 3. And 3 to 2 is 5. Yeah, this is also updated now. And we are getting this 3. Okay. Now all are updated. Now in the remaining one, 5, 6, and 4. This is the smallest.
6.
Yeah,
I'll go for 6. Yeah.
6. So now this is the next traversed, and this we are getting from 3. Okay, so this is now added. And from 6.
And there is only one logical thing, that is 5 followed by 2.
But this is already 6. Okay.
Yeah.
And again we are getting 6. So no need to update. So that means more MST is possible in this case, because 6 we are getting from another this 3, but still we are also getting from 6. So that is actually just giving this information more than one MST are possible. Suppose we are not updating this because we have already 6. So that is from 3. So no updation is happening. Now 5 and 6.
5 and 2, right?
sorry, I'm just telling this distance. Okay,
Ah,
2
okay,
and 5. Okay, 2 and 5. So which one have the minimum? This 2. Okay, now
Yeah.
this is now selected. So this edges we are also getting from this side. 3.
Sorry. Wait a minute. 2, yes, it has 5, but 2 is not connected to 6, isn't it? So I don't need to go to, I mean, from 6.
No, here
shouldn't
we are
I
not.
traverse
We are not finding any path. We are just picking the edge that will
which is the
connect
lowest
all
weight?
the
Okay,
nodes. That
okay,
will connect
okay,
all the nodes.
okay.
Okay. So this 5 we are getting now. This is the updated one, and
Yeah.
from this 2 nodes, we are
Node 2,
getting 3. You can
3.
see we are
Yeah.
getting 3.
For 5.
So that means this will be updated by 3, and this is from 2.
Yeah.
Okay. Now next selected only this is remaining. So this will be the 5 selected one, and out of these, so we will select this, and we are getting from this side.
So it's not the path; it is the weight every time, and the
Yeah.
weight,
So
weight
this
updated
is
to
the
least. Okay.
now this connection is actually representing the minimum spending tree. So total cost is 5 plus 5 plus 5 plus 3 plus 4. Total 15, 18, and 22. And this.
And the number of path when we are talking about, can we also determine the number of paths from here?
No, you will always get only one path to each node.
Okay. Okay.
Here we are not finding out the path things. We are connecting only with the minimum total cost.
Okay, sorry, I am referring to the question that Rahul was showing in the earlier classes, where he was writing it as alpha and beta. That was for this problem, or
Alpha and beta.
would you
I
be
think
able to?
okay. So I think alpha is representing the cost, and maybe beta is representing the total number of spanning tree.
Correct.
Correct, no?
Yes.
Okay. So in that case, you have to figure out that what is the minimum cost and what are the total number of spanning tree possible. So here we can see we always pick the smaller one. So okay. So this 6 is also not selected. Okay. So for this question, I think we have only one
spanning tree
MST possible, because 3 and 4 is selected and remaining all 3 5s are selected.
Okay.
So we have already discussed this, no? Okay.
Yeah.
So
Yeah,
only one
and
MST is
if
possible.
weights are the same for 2 of them, we'll take the least number, is it? Least vertex. Okay. Okay.
Yes.
All right. All right. Thank
Okay.
you.
So that question is actually you have to calculate the both things. First, this
Yeah.
is cost and
Yeah.
number of MST. Then you will add this.
Yeah. All right.
Okay.
Thank you. Thank you very much.
Yeah, this
Thank
is
you
the
very much.
question. Okay. So I think all done. Okay. Any query from anyone?
One
So,
last
sir, the
request
last
is
question.
the questions that you actually shared in the PPT. Please do not erase the comments or whatever you had written on that. The
Oh, that
answers are
PDF?
there. Yeah, the PDF.
Okay.
Keep it the way it is. It will be a reference.
Okay, I will
for
save
at
this
least
as
those
it
who,
is.
yeah.
So the last question in the mock.
Last question in the mock.
Mock
Okay.
two, yes.
This one. 16th one. Hello. Hello.
Yes, sir. Yes, sir.
Okay.
Yes, sir. That was the question.
Okay. So this topic is discussed in the week 8. Okay. In the recursion tree topic. Okay. Check this. So for this, one recurrence is given, okay, and 9. This is given like this. So T1 equal to 9 T1 n by 3 plus big O n. So how we can create a recursion tree for this? So that means T1. Okay, so T1 is starting. So like T1 n, and after that this is divided into 9 child. Okay, 9 times like this. And each problem have with the size t n by 3, correct? Okay, like this, 9 times. And when we are dividing into the 9 recursive call, we the apart from that calls, we have the time order of n for this. Okay, so this is the recurrence format. So for Tn, our algorithm is taking order of n time apart from the recursive calls, non-recursive calls. If our input is n, if our input is n by 3, so definitely this will also be n by 3. So for only this part, okay, just look only this part. This is a separate problem, T n by 3. So when you expand this, you will get 9 times T n by 9, correct?
N by 9.
And big O n by
plus O
3.
by 9. O by 3.
Okay, like this. So
O n by 3.
Same value we are writing here. So we can also ignore this big O things or number of steps we are writing. N by 3, okay? So n by 3, it will take n by 3, it will take, so all 9s will take n by 3. So we can write total number of times on this level is 9 into n by 3, correct? So this was at the previous level, this was n, but this time this is 9 by 3. So total 3 into 3. So we will cut this, so it will become 3n. Okay. Now next level, again one call will be divided into 9 times, okay, and with the size of T n by 9, correct? This T n by 3 I have mentioned here, so this you can see 9 times, this is divided n by 3, 9. So n by 9, 9 times for this, similarly for this 9 times, okay? 9 times. So for all 9 child, we have 9 into 9.
81.
Okay, so for each time, so we will, if you add total child we have at this level is 81. And each have the size n by 9. Correct? So it become 9 and it is a 3 square. Correct? So you can just observe this. The number of operation at each level are increasing.
Yes.
Correct? So this is n, then 3 to the power 1 n, then 3 to the power 2 n. So some constant this amount this number of operations are increasing. So in big 8, that condition is given. If the number of operation at each level are increasing, then how you can figure out the complexity directly. So if you remember this, so let me open the slides. So one second. That big 8. You can see these 3 conditions is discussed, okay? Decreasing, equal and increasing, last 3 condition. So in the case of increasing, we can directly write the complexity in this manner. Tn equal to big O n log Cr. And what are these C and what are these R actually? So R is a recursive call and C is a divided value. So in the original expression, which is this one, this R is actually a 9 and C is actually a 3. Okay, R is a recursive call and this C is a dividing value. So you can simply write the complexity big O and log. Okay, and C is the base, so C become 3 and this R become 9 here. Okay, and what will be the value then? Big O and
2.
And, so this will become 3 to the power 2 and 2 will come at the place, so 2 into 1. Okay, and it will become big O n square. Okay, for first expression, it will become n square complexity.
Okay.
Okay, and for second expression, just check in similar way. So 4t, so this time n square is given. Okay. Once again, just look this. So t n we have, and this time 4 child, and each have n by 4, n by 4, n by 4, n by 4, and this time we are getting n square at this level, but next level we have n by 4, that means 4 into n square by 16, correct? I'm just making this square. So we are getting this value 4 divided by this 4. So this is n square by 4 at this level. So in next level you will get again, so this n by 16, okay, t like this, and 4 times, and similar for 4 times for this, 4 times for this, 4 times for this. So total 16 into, now n square divided by 16 square. Okay, so this will become n square by 16. So this time this lower value is increasing. So this is now 4 to the power 1. Now it becomes 4 to the power 2 in this manner. So you can see this time the value is decreasing. Correct? At every level, this value is, initially this was n square. Now this become n square by 4. Now next level is it become n square by 16.
N square by 16.
So this value is now decreasing. So in the case of decreasing, just use this formula, direct Tn equal to big O Fn. And what is our Fn in this equation? This Fn is this last one. Okay, this is called as a Fn. This is Fn. And here in the second expression, this is Fn. Okay, so you can directly write the complexity Tn equal to big O Fn. And that means big O n square. So this will become the complexity for second expression. So that means this option is correct. Both expression we are getting the n square.
Okay.
Okay. So yeah, you can just remember these 3 conditions and just decreasing, increasing, or equal. In the case of equal, just use Fn log n. If each level our number of steps remains same, then directly put the Fn equal to log n. Fn into L log n, sorry. Okay.
So the previous page.
Previous page for
where you had done the calculation.
So whatever we are writing on the extreme right is whatever is there as big O of in that particular equation. In the second case, it is n square, and the first case it is n.
Yeah, actually in our expression, what are the terms actually? T and this is called as a R, okay, and T, n by C, and plus Fn. This is the equivalent things. Okay, so this R or capital R or small r is represent the number of recursive calls.
Yeah.
And this is the divide part, how we are dividing, and this is say Fn, what time is taking. So just make this in the put these things in the formula. Okay.
Okay.
Okay. Thank you, sir.
Okay.
Thank you very much. Thank you. Thank you for your patience.
Thank you.
Sir.
Yeah. Yeah, Rohini.
Yes, thank you, sir.
Okay.
Thank you, sir. Good night.
Okay, thanks everyone. Good night.
Thank you. Good night.
Good night.
Thank you, sir.
Good night.